We live in a universe we cannot see the end of. We ask questions not because we expect easy answers, but because we cannot help but wonder. Tonight we follow one of the biggest questions of all. Is there something beyond the universe? Our cosmos stretches vast and silent around us, filled with countless stars and galaxies drifting through the darkness. As we gaze upward on clear nights, we glimpse only the tiniest fraction of what exists. The universe holds secrets beyond our imagination, mysteries that whisper from the void. What happens at the edge of everything? Is there an edge at all? Does our universe have a boundary? And if so, what lies on the other side? These questions have haunted philosophers and scientists for millennia, pulling at our minds like gravity itself. The answers may forever elude us. We are bound within this cosmos, limited by the speed of light and the vast distances between objects. Yet still we wonder, still we dream, still we reach outward with our telescopes and equations, hoping to glimpse something beyond the veil. Tonight, we journey together through what we know about our universe, what we suspect, and what remains pure speculation. We will travel from the familiar planets of our solar system to the farthest observable galaxies and then beyond, into realms where physics meets philosophy. This is not a journey with a clear destination. Rather, it is an exploration of possibilities, a meditation on the nature of existence itself. As we drift through the cosmos together, we invite you to ponder these ancient questions with fresh eyes. Is our universe all that exists? Or is it merely one bubble in an infinite foam? Is it a single page in an endless book? Or perhaps a hologram projected from some higher dimension? The stars above do not answer. They simply shine, sending their light across impossible distances to reach our eyes. In that silence, in that vastness, we find both our greatest questions and our deepest peace. Let us begin our journey not with certainty, but with wonder, not with answers, but with better questions. For in the space between knowing and unknowing, we find the most human place of all, curiosity. The night sky has always been our first window into the unknown. Ancient peoples looked up and saw patterns, stories written in starlight. They imagined the heavens as a dome, a celestial sphere enclosing our world. What lay beyond that sphere? Gods, perhaps, or other realms beyond mortal comprehension. Each culture created its own cosmology, its own explanation for what might exist beyond the visible. The Greeks imagined crystalline spheres carrying the planets and stars in their eternal orbits. Medieval thinkers placed God and the heavenly hosts in the space beyond the stars. For much of human history, the edge of the universe was thought to be just above the highest clouds, or perhaps just beyond the orbit of Saturn, the most distant planet visible to the naked eye. But as our tools improved, as our understanding deepened, the universe expanded. Telescopes revealed planets beyond Saturn. Stars proved to be distant suns, not points of light fixed to some cosmic ceiling. Galaxies emerged from the darkness, island universes containing billions of stars, scattered across unimaginable distances. With each discovery, the edge receded. With each new understanding, the boundary between known and unknown shifted outward. Yet always the question remained: if the universe has an edge, what lies beyond it? Perhaps more fundamentally, what do we mean by universe? If the universe is truly everything that exists, then by definition, nothing can be beyond it. And yet, modern physics suggests possibilities that challenge our very definition of existence itself. As we float through space tonight, cradled in the arms of gravity, we invite you to relax, to breathe deeply, to let your mind expand like the cosmos itself. Feel the vastness around you. Feel the questions that have no easy answers. Feel the wonder that comes from acknowledging both our curiosity and our limitations. The stars above us are ancient lights. Some began their journey toward Earth before our species existed. Some shine from galaxies so distant that the light we see tonight left them when dinosaurs still walked the Earth. We see not just across space, but across time itself. And beyond the farthest star we can see, beyond the most distant galaxy our telescopes can detect, what waits in that darkness? Is it more space, more galaxies, more of the same? Or is it something else entirely? Something our mathematics hints at, but our minds struggle to comprehend. Tonight, we will not claim to know what cannot be known. We will not pretend certainty where none exists. Instead, we will journey together to the edge of understanding, to the boundary between knowledge and mystery. And from that vantage point, we will gaze outward, into possibilities. For now, close your eyes if you wish. Imagine yourself drifting among the stars, weightless, timeless. The questions will wait. The universe will wait. We have all night to wonder together, to dream together, to explore the greatest mystery of all. What, if anything, lies beyond all we know? Is there something beyond the universe? Let us find out together, one star at a time, one question at a time, one moment of wonder at a time. Before we ask what's beyond, we must understand what's within. The word universe comes to us from Latin, where uni means one and versus refers to a turning or a direction. One turning, one wholeness, the entirety of existence turning together as a single entity. But what does that mean in scientific terms? What exactly is this universe we inhabit? At its simplest, cosmologists define the universe as the totality of all space, time, matter, and energy. Everything that exists, has existed, or will exist. Every galaxy, every star, every planet, every atom, and every quantum particle. The vacuum between stars, the dark matter we cannot see, the dark energy that pushes space itself apart. All of it together forms what we call the universe. But there's an important distinction here, one that will become crucial as we explore our central question. There is the observable universe, which is everything we can potentially detect from our vantage point on Earth. And then there is the entire universe, which may extend far beyond what we can observe. This is not merely a philosophical distinction. It emerges naturally from the fundamental laws of physics, particularly the cosmic speed limit, light. Nothing can travel faster than light. This is not just a current technological limitation, but a fundamental rule of nature according to Einstein's theory of relativity. Light travels at approximately 300,000 kilometers per second, an almost incomprehensible speed. At this velocity, light could circle our Earth 7.5 times in a single second. Yet despite this incredible speed, the universe is so vast that light from distant objects takes billions of years to reach us. The light from our sun takes about 8 minutes to reach Earth. The light from the nearest star beyond our sun, Proxima Centauri, takes 4.25 years. The light from the Andromeda Galaxy, our closest neighboring major galaxy, has traveled for approximately 2.5 million years before entering our telescopes. And the most distant objects we can observe, their light has been traveling for almost the entire history of the universe itself, nearly 14 billion years. This sets a fundamental limit on what we can observe. We cannot see anything whose light hasn't had time to reach us since the beginning of the universe. This creates a boundary around us, a cosmic horizon beyond which we cannot see. But this doesn't mean nothing exists beyond that horizon. In fact, our best understanding of cosmic evolution suggests that the universe almost certainly extends far beyond what we can observe. How far? That remains one of the greatest unknowns in modern cosmology. The universe began approximately 13.8 billion years ago in the event we call the Big Bang. This wasn't an explosion in space, as the name might suggest. Rather, it was the beginning of space and time themselves. Before the Big Bang, there was no where for anything to exist, no when for events to occur. In the first fraction of a second after the Big Bang, the universe expanded at an incredible rate, a process called cosmic inflation. Space itself stretched, carrying energy with it. As the universe cooled, this energy began to condense into particles, first quarks and gluons, then protons and neutrons, and eventually, after hundreds of thousands of years, atoms formed. Over billions of years, these atoms gathered into clouds of gas, which collapsed under gravity to form the first stars. Stars gathered into galaxies. Galaxies formed clusters and superclusters, creating the cosmic web of structure we observe today. All of this happens within space, but space itself is not static. It continues to expand, carrying galaxies along with it like raisins in rising bread dough. The galaxies themselves aren't moving through space as much as space itself is stretching between them. This expansion has profound implications for our question about what lies beyond the universe. If space itself is expanding, what is it expanding into? Is there something beyond space, some metaspace that contains our universe? Or is this question itself meaningless, a category error born from our limited three-dimensional thinking? The universe may be finite or infinite in extent, It may have a boundary, or it may loop back on itself in higher dimensions, making it boundless yet finite, like the surface of a sphere. Our observations so far cannot definitively answer these questions. When we contemplate the universe, we must also consider time as an intrinsic dimension. The universe is not just a place, it is an ongoing process, a four-dimensional reality with time woven into its very fabric. We cannot separate where from when at the cosmic scale. Quantum physics further complicates our picture, suggesting that at the smallest scales, reality becomes probabilistic rather than deterministic. Particles exist in states of possibility until observed or measured. Some interpretations of quantum mechanics suggest that all possible outcomes actually occur, branching into separate realities, separate universes. So when we ask, what is the universe? We must acknowledge that the answer depends on our frame of reference, our scale of observation, and even the theories we use to interpret what we see. For tonight's journey, we will primarily consider the universe as cosmologists do, the entirety of space and time and all they contain. But we will keep in mind that this definition itself may be limited by our current understanding, our current mathematics, our current imagination. The universe is everything we know exists, but is that all that exists? That is the question that drives us forward, that pulls us toward the cosmic horizon and asks us to peer beyond into the unknown. Consider for a moment the scales involved in our universe. Our home planet, Earth, seems vast to us as we walk its surface. Yet Earth is merely a tiny speck orbiting an average star we call the Sun. This star, impressive as it is, represents just one among hundreds of billions in our galaxy, the Milky Way. And the Milky Way itself, a single galaxy among an estimated 2 trillion galaxies in our observable universe. Each galaxy contains its own collection of stars, planets, nebulae, black holes, and other cosmic structures. Some are spiral galaxies like our own, with elegant arms curling outward from a bright central core. Others are elliptical, irregular, or take on strange and beautiful forms as they interact and merge with their neighbors. The spaces between galaxies are not empty either. Vast filaments of dark matter form an invisible cosmic web, guiding the formation and evolution of visible structures. Hot gas fills the space between galaxy clusters, so hot it glows in X-ray light invisible to human eyes but detectable by our specialized telescopes. And between all these structures lies the vacuum of space, which isn't truly empty at all. Quantum physics tells us that even perfect vacuum seethes with virtual particles popping in and out of existence, borrowing energy from the fabric of reality itself for the briefest of moments. Our universe is also defined by its fundamental forces. Gravity, the weakest yet most far-reaching force, shapes the largest structures in the cosmos. Electromagnetic force governs light, electricity, magnetism, and the interactions between atoms. The strong nuclear force binds protons and neutrons together in atomic nuclei, while the weak nuclear force facilitates certain types of radioactive decay and plays a crucial role in stellar fusion. These forces, along with the particles they affect, comprise what physicists call the Standard Model. But even this sophisticated framework has its limits. It doesn't fully incorporate gravity. It doesn't explain dark matter or dark energy. It doesn't tell us why our universe has the particular properties it does, rather than some other set of properties. This brings us to another fascinating aspect of our universe, its apparent fine-tuning. Many fundamental constants of nature seem precisely calibrated to allow for the emergence of complexity, of stars and planets, of chemistry, and eventually life. If the strong nuclear force was slightly weaker, atoms beyond hydrogen couldn't form. If gravity was slightly stronger, stars would burn too quickly for life to evolve on their planets. Some see in this fine-tuning evidence of design, of purpose. Others suggest it may be an observational bias. We can only exist in a universe compatible with our existence. So of course we find ourselves in such a universe, regardless of how many others might exist with different properties. And here we find another definition of universe. Not just all that exists, but the specific realm characterized by our particular set of physical laws, constants, and conditions. Could there be other regions beyond our cosmic horizon where physics itself operates differently? This question leads us toward multiverse theories, which we'll explore later in our journey. The universe as we understand it also has a history, a biography written in the light of ancient stars, in the cosmic microwave background radiation that fills all space, in the abundance of elements forged in stellar furnaces and scattered by supernovae. We live approximately 13.8 billion years after the Big Bang, in what cosmologists call the stelliferous era, the age of stars. Before this came the primordial era, when matter first formed and the universe was too hot and dense for stars to shine. After our current era will come the degenerate era, when star formation ceases and white dwarfs, neutron stars, and black holes dominate the cosmos. Later still, the black hole era will see even these massive objects evaporate through Hawking radiation. And finally, in the distant future, measured in numbers too large to comprehend, the dark era may arrive, when all organized matter has dissolved into low-energy radiation and elementary particles. This cosmic timeline stretches from the infinite energy density of the Big Bang to the near absolute zero of the far future. We exist in a thin slice of time when the universe is cool enough for complex structures, yet hot enough for ongoing processes of creation and change. Our universe is also characterized by its fundamental asymmetries. There appears to be more matter than antimatter, though our theories suggest they should have been created in equal amounts. Time flows in one direction, from past to future, despite most physical laws working equally well in either direction. Entropy, the measure of disorder in a system, always increases over time in closed systems, giving us the arrow of time we experience. These asymmetries and many others shape the universe we observe. They determine what is possible and what isn't, what can exist and what cannot. They define the boundaries of reality as we know it. But do they define all reality? Or might there be realms beyond our universe where different rules apply, where time flows differently or doesn't flow at all, where space has more dimensions or fewer, where the very concept of existence takes on meanings we cannot currently comprehend? These questions take us to the edge of science, to the boundary where physics meets philosophy, where mathematics meets metaphysics. They remind us that our understanding of the universe, sophisticated as it is, remains incomplete. The universe is also defined by what we don't know about it. Dark matter makes up approximately 27% of its mass energy content, yet we cannot directly observe it. Dark energy comprises about 68%, accelerating the expansion of space for reasons we don't fully understand. Together, these mysterious components account for 95% of everything that exists. The stars and galaxies we see, the planets and people and all visible matter, represent merely 5% of the cosmic inventory. We live in a universe far stranger than our ancestors could have imagined. Quantum entanglement allows particles to influence each other instantaneously across vast distances. Black holes warp space-time so severely that not even light can escape their gravitational pull. The fabric of space itself ripples with gravitational waves produced by colliding neutron stars and black holes, events so violent they momentarily outshine entire galaxies. This is our universe, a realm of light and dark, of known and unknown, of elegant mathematical patterns and perplexing exceptions. It is everything we can observe, everything we can detect, everything whose effects we can measure. But is it everything, full stop? Or is our universe itself just one part of something larger, something more encompassing, something truly beyond? To explore that question, we must first understand the boundaries of our cosmic vision, the limits of what we can observe from our vantage point on this small blue planet orbiting an ordinary star in an ordinary galaxy. We must explore the observable universe, that sphere of space and time whose light has had time to reach us during the 13.8 billion years since the Big Bang. We must understand this cosmic horizon not as the edge of all existence, but as the edge of our vision, the limit of what we can currently see. Beyond that horizon lies more universe, almost certainly. But how much more? And is there something else beyond even that? These questions pull us forward into the darkness, into the unknown, into the greatest mystery of all. Before we ask what's beyond the universe, we should perhaps ask another question. How do we know where the universe ends? How do we define its boundary, its edge, its limit? To answer that, we must look outward, to the farthest reaches of the observable cosmos. Beyond the farthest star we can see, space may still continue. When we speak of the observable universe, we're referring to a specific volume of space. It's not the entire universe, but rather the portion we can theoretically detect from our vantage point on Earth. It's a sphere centered on us, with a radius of approximately 46.5 billion light-years in every direction. This number might seem puzzling at first. If the universe is only 13.8 billion years old, how can we see 46.5 billion light-years away? Wouldn't the light from such distant objects not have had time to reach us? The answer lies in the expansion of space itself. The light from the most distant observable objects began its journey toward us nearly 13.8 billion years ago, shortly after the Big Bang. But during that journey, the space between those objects and us has been stretching, expanding. The objects themselves have been carried much farther away by this cosmic expansion than their light has been traveling. It's like walking on a moving sidewalk that's going in the opposite direction. You might walk 5 kilometers, but end up much less than 5 kilometers from your starting point, because the sidewalk itself is moving backward. So our observable universe is a sphere with a radius of 46.5 billion light-years, centered on Earth. Any object currently beyond that distance, even if it emitted light the moment after the Big Bang, has not had sufficient time for that light to reach us. The expansion of space has carried them beyond our cosmic horizon. This cosmic horizon is not a physical boundary in space. It's an observational limit, a consequence of the finite age of the universe and the finite speed of light. As time passes, more distant regions become visible to us as their light finally completes its long journey to Earth. Our observable universe grows larger with each passing second. But what's actually within this enormous sphere? What does the observable universe contain? First, there's our home, the solar system. 8 planets orbiting an average-sized star we call the Sun, along with numerous dwarf planets, moons, asteroids, comets, and other small bodies. This entire system spans only about 9 light hours across, a tiny fraction of a light year. Beyond our solar system lies our galaxy, the Milky Way, a vast spiral of stars, gas, and dust, spanning approximately 100,000 light-years from edge to edge. It contains between 100 billion and 400 billion stars, many with their own planetary systems. But the Milky Way is just one galaxy among many. Our nearest major galactic neighbor, the Andromeda Galaxy, lies about 2.5 million light-years away and is slightly larger than our own. Together with about 50 smaller galaxies, the Milky Way and Andromeda form what we call the local group. The local group, in turn, is part of the Virgo supercluster, a collection of galaxy groups and clusters spanning approximately 110 million light-years. And the Virgo supercluster is now understood to be just one lobe of an even larger structure called the Laniakea supercluster, which contains approximately 100,000 galaxies spread across roughly 500 million light-years. These structures, immense as they are, represent just a tiny portion of the observable universe. Astronomers estimate that the observable universe contains approximately 2 trillion galaxies, each home to billions or even trillions of stars, and potentially even more planets. Between these galaxies lies the intergalactic medium, a tenuous gas primarily composed of hydrogen and helium. This medium is not evenly distributed, but follows the cosmic web, a vast network of filaments and walls of dark matter that guide the formation and evolution of visible structures. At the largest scales, the universe appears remarkably uniform. This is a cornerstone of modern cosmology, the cosmological principle, which states that on sufficiently large scales, the universe looks essentially the same in all directions and from all locations. There are no special places, no centers, no edges within the universe itself. This uniformity is visible in the cosmic microwave background radiation, the faint afterglow of the Big Bang that permeates all of space. This radiation appears almost perfectly uniform in all directions, with tiny temperature variations of just 1 part in 100,000. These minute variations are the seeds from which all cosmic structure grew, the earliest imprints of what would eventually become galaxies and galaxy clusters. As we peer deeper into space, we also look further back in time. The light from distant galaxies shows us not how they appear today, but how they appeared when that light began its journey toward us, millions or billions of years ago. The most distant objects we can observe appear to us as they were just a few 100 million years after the Big Bang. These earliest galaxies look very different from the mature spiral and elliptical galaxies we see closer to home. They're smaller, more irregular, and forming stars at a furious pace. We're witnessing galaxy evolution in its earliest stages. Even more distant than these young galaxies is the cosmic microwave background radiation itself, which shows us the universe as it was just 380,000 years after the Big Bang. Before this time, the universe was an opaque plasma of electrons and protons, too hot and dense for light to travel freely. This radiation represents the oldest light in the universe, the most distant thing we can observe with electromagnetic waves. There is, however, another window into the early universe: neutrinos. These ghostly particles interact very weakly with matter and should have decoupled from other particles when the universe was just 1 second old. In principle, if we could detect the cosmic neutrino background, we could see the universe at an even earlier stage. Similarly, gravitational waves might someday allow us to probe the first fractions of a second after the Big Bang. But despite these amazing observational capabilities, there are fundamental limits to what we can see. The observable universe is finite, not because the universe itself is necessarily finite, but because light has had only 13.8 billion years to travel since the beginning of time as we understand it. Beyond the cosmic microwave background lies what cosmologists call the surface of last scattering, the moment when the universe first became transparent. And beyond that, in principle, there should be more universe, more space filled with matter and energy, but we cannot directly observe it with any form of electromagnetic radiation. This brings us to a profound realization: the observable universe is just a subset of the entire universe. It's the portion we can see from our particular vantage point at this particular moment in cosmic history. Every observer in the universe, regardless of their location, has their own observable universe centered on them. These observable universes overlap significantly for nearby observers, but become increasingly distinct for distant ones. An observer in a galaxy 10 billion light-years away sees a completely different set of distant objects than we do. Their cosmic horizon encompasses regions of space forever hidden from our view, while some regions visible to us lie beyond their horizon. This means that when we speak of the universe, we must be careful about which universe we mean. Do we mean just the observable universe, the sphere of space whose light has had time to reach us? Or do we mean the entire cosmos, including regions beyond our observational horizon? Most cosmologists believe that the universe extends far beyond what we can observe, perhaps infinitely far. This belief is rooted in the cosmological principle, the observed large-scale homogeneity and isotropy of space, and our current understanding of cosmic inflation, the period of extremely rapid expansion in the earliest moments after the Big Bang. Inflation theory suggests that our observable universe emerged from just a tiny patch of a much larger inflating space. Most of that space continued to inflate and remains forever beyond our view. If this theory is correct, the actual universe might be vastly larger than the part we can observe, perhaps even infinitely larger. But we should be careful about making definitive statements. Science deals with what can be observed, measured, and tested. The regions beyond our cosmic horizon cannot be directly observed, at least not with current methods. Any claims about what exists beyond must be inferred from theoretical models, which, while mathematically rigorous and consistent with observations, remain models rather than direct observations. This tension between what we can observe and what might exist beyond our observational limits lies at the heart of our exploration. It reminds us that the boundary of the observable universe is not the edge of all existence, but merely the limit of our cosmic vision. The observable universe, vast as it is, represents only a finite volume of space and a finite period of time. It contains a finite number of atoms, a finite number of stars, a finite number of galaxies. Large numbers, to be sure, approximately 10 to the power of 80 protons and neutrons, for instance, but finite nonetheless. If the entire universe is also finite, then it too contains a finite amount of matter and energy, just more than we can currently observe. But if the universe is infinite, as many cosmologists suspect, then it contains an infinite amount of matter and energy distributed across an endless expanse of space. an infinite universe would have profound implications. In a truly infinite universe with a random but non-zero distribution of matter, anything that can happen will happen, not just once but an infinite number of times. There would be an infinite number of Earths, an infinite number of galaxies identical to the Milky Way, an infinite number of individuals identical to you, reading these very words at this very moment. This concept, sometimes called the infinite monkey theorem in a more limited context, emerges naturally from the combination of infinity and probability. Given an infinite canvas, any pattern with a non-zero probability must appear and appear infinitely many times. But we should be cautious about such speculation. Infinity is a mathematical concept that our finite minds struggle to comprehend. The observable universe, while enormous, is decidedly finite. Whether the entire universe is finite or infinite remains an open question in cosmology. What we do know is that the observable universe has a center and an edge, defined not by any physical boundary, but by the limitations of light travel time. We, the observers, are always at the center of our observable universe. This is not because we occupy any special place in the cosmos, but simply because our observable universe is defined by what we can see from our location. The edge of the observable universe is called the particle horizon. It marks the current distance to the farthest objects whose light has had time to reach us since the beginning of the universe. This horizon is not static. It expands at the speed of light as the universe ages, bringing more distant regions into view with each passing moment. There is another horizon worth mentioning, the event horizon. While the particle horizon defines what we can see now, the event horizon defines what we will ever be able to see in the future, even given an infinite amount of time. Due to the accelerating expansion of the universe, some distant objects are receding from us faster than the speed of light when we account for the expansion of space itself. Light emitted from these objects now will never reach us, no matter how long we wait. This cosmic event horizon currently lies at a distance of approximately 16 billion light-years. Any object currently beyond that distance is forever beyond our reach, its future light unable to overcome the expanding gulf of space between us. As the universe continues to expand at an accelerating rate, this horizon will gradually shrink, isolating us ever more completely from the wider cosmos. So we find ourselves in a universe that is observable only in part, with regions that we can see now, regions that we will be able to see in the future, and regions that we will never be able to see, all determined by the complex interplay of light speed, cosmic age, and accelerating expansion. The observable universe, then, is not just a volume of space, but a four-dimensional bubble in space-time, expanding outward from our location at the speed of light in all directions and all times. It is our cosmic light cone, the set of all events in space-time that can be causally connected to us through the exchange of light signals. Within this light cone lie all the stars and galaxies we can see, all the cosmic structures that have formed over billions of years, all the complex chemistry and perhaps biology that has emerged on countless worlds throughout the cosmos. It is vast beyond human comprehension, yet still limited, still finite, still just a portion of what may exist beyond. The observable universe reminds us of both the incredible reach of our observations and their fundamental limitations. We can see billions of light years in every direction, peer back billions of years in time, detect thousands of exoplanets around distant stars, and map the cosmic web of dark matter through its gravitational effects. Yet we remain confined to our cosmic horizon, unable to directly observe what lies beyond. This limitation is not a failure of technology or imagination, but a consequence of the fundamental physics of our universe. It reminds us that even with perfect instruments and infinite patience, there would still be regions of space forever hidden from our view. Does this mean we can never know what lies beyond the observable universe? Not necessarily. While direct observation is impossible, we can make reasonable inferences based on what we observe within our horizon and our understanding of physical laws. The remarkable uniformity of the cosmic microwave background radiation suggests that regions of space far beyond our horizon are likely similar to those we can observe. The success of cosmic inflation theory in explaining the flatness, homogeneity, and isotropy of our observable universe provides a framework for understanding how much larger the entire universe might be. Some theoretical models suggest that our observable universe may be just one bubble in a vast multiverse, regions of space that underwent inflation at different times or with different physical parameters. Others propose that the universe might be finite but unbounded, like the surface of a sphere in higher dimensions, allowing for the possibility that a traveler moving in what seems like a straight line might eventually return to their starting point. These ideas remain speculative at the frontier of modern cosmology. They remind us that the observable universe, vast as it is, may be just a tiny fraction of all that exists. Beyond the farthest star we can see, beyond the most distant galaxy our telescopes can detect, space may continue, perhaps forever, filled with more stars, more galaxies, more worlds, more possibilities than we can currently imagine. The observable universe sets the limits of what we can directly know through observation, but it does not set the limits of what we can theorize, what we can mathematically model, what we can philosophically contemplate. In pushing against this cosmic horizon, in asking what might lie beyond, we engage in one of the most profound scientific and philosophical inquiries possible. What lies beyond the observable universe? More universe, almost certainly. But how much more? And is it all the same? Or might there be regions where the very laws of physics differ from our own? These questions lead us to consider not just the extent of space, but its shape, its geometry, its fundamental nature. Space may be curved, but if it loops, where does it begin and where does it go? When we contemplate what might lie beyond the universe, we must first understand the shape of space itself. This isn't as straightforward as it might seem. Space is not merely an empty container in which objects exist. According to Einstein's general relativity, space is a dynamic entity, a fabric that can stretch, bend, and warp in response to mass and energy. The geometry of space determines how objects move through it, how light travels across cosmic distances, and potentially whether the universe has a boundary at all. Cosmologists consider three basic possibilities for the large-scale geometry of our universe: flat, open, or closed. A flat universe is perhaps the easiest to visualize. It follows the familiar rules of Euclidean geometry that we learn in school. Parallel lines never meet. The interior angles of a triangle always sum to 180 degrees, and the circumference of a circle is always 2 pi times its radius. If you were to draw a huge triangle between three distant galaxies in a flat universe, its angles would add up to exactly 180 degrees. In a flat universe, space extends infinitely in all directions. It has no boundary and no edge. If you could travel in a straight line forever, you would never return to your starting point. You would simply continue onward, encountering new regions of space indefinitely. An open universe has what mathematicians call negative curvature. You can visualize this as a saddle shape or a hyperbolic surface. In such a universe, parallel lines diverge, and the angles of a triangle sum to less than 180 degrees. Space expands faster than in a flat universe, and like the flat case, an open universe is infinite in extent. A closed universe, by contrast, has positive curvature, like the surface of a sphere. In this geometry, parallel lines eventually converge, and the angles of a triangle sum to more than 180 degrees. A closed universe is finite yet boundless. It contains a finite volume of space and a finite amount of matter, yet it has no edge or boundary. This concept of a boundless yet finite universe can be difficult to grasp. The standard analogy is the surface of a sphere. If you're an ant living on the surface of a sphere, you can walk forever in any direction without ever reaching an edge. The surface is finite in area, yet it has no boundary. Our three-dimensional space could theoretically have an analogous property in 4 dimensions. In a closed universe, if you could travel far enough in one direction, you would eventually return to your starting point, having circumnavigated the entire universe. Light would also follow these curved paths, potentially allowing us to see multiple images of the same distant objects in different directions, or even to see the back of our own galaxy. So which of these geometries describes our universe? For decades, cosmologists have sought to measure the curvature of space using various observational techniques. The most precise measurements come from the cosmic microwave background radiation, the afterglow of the Big Bang that fills all of space. By mapping tiny temperature fluctuations in this radiation, missions like WMAP and Planck have measured the geometry of space with unprecedented precision. The results indicate that our universe is remarkably close to flat, with any curvature being so slight as to be nearly undetectable with current methods. This flatness poses an interesting puzzle for cosmologists. In the early universe, even a tiny amount of curvature should have been amplified over time by the expansion of space. The fact that the universe remains so close to flat today suggests that it must have been extraordinarily flat in its earliest moments, requiring an explanation for this apparent fine-tuning. Cosmic inflation theory provides such an explanation. According to this theory, the universe underwent a period of exponential expansion in the first fraction of a second after the Big Bang. This rapid stretching would have flattened any initial curvature, much as inflating a balloon makes its surface appear increasingly flat from the perspective of a tiny observer on that surface. If our universe is indeed perfectly flat, as current observations suggest, then it is likely infinite in extent. Space would continue forever in all directions, containing an infinite number of galaxies, stars, and possibly even civilizations, all subject to the same physical laws we observe in our cosmic neighborhood. However, we should be careful not to confuse geometry with topology. Geometry describes how space curves, while topology describes how it connects. Even a flat universe could have an interesting topology that causes it to connect back on itself, creating a finite volume despite its flat geometry. Imagine a flat piece of paper. Its geometry is Euclidean, following the rules of flat space. But if you connect the left edge to the right edge and the top edge to the bottom edge, you create what mathematicians call a torus, or donut shape. The geometry remains flat at every point, yet the space is now finite and has an interesting connectivity. If you move far enough in one direction, you return to your starting point. Our three-dimensional space could theoretically have analogous properties, connecting back on itself in various ways while maintaining its flat or nearly flat geometry. There could be a cosmic topology that makes the universe finite despite its flat geometry. If this were the case, traveling far enough in one direction would eventually bring you back to your starting point. Light would also follow these paths, potentially creating multiple images of the same distant objects in different directions. Astronomers have searched for such repeating patterns in the cosmic microwave background and in the distribution of galaxies, but so far no compelling evidence has been found. The current consensus among cosmologists is that our universe is either perfectly flat and infinite, or so close to flat that any curvature or interesting topology lies beyond our observable horizon. But this consensus is based on limited observations and could change with new data or theoretical insights. The shape of space has profound implications for our central question: is there something beyond the universe? If the universe is indeed infinite and flat, then there is no beyond in the spatial sense. Space simply continues forever in all directions. There is no edge to go beyond, no boundary to cross, no exterior to explore. But if the universe is closed and finite, like the surface of a hypersphere, then the concept of beyond becomes more complex. In one sense, there is still no beyond, as the universe loops back on itself without any boundary. But in another sense, we could conceive of a higher dimensional space in which this hypersphere is embedded, a space outside our three-dimensional universe. This higher dimensional embedding space is not necessarily physical. It might be merely a mathematical construct that helps us visualize the curvature of our space. But some theories in modern physics, particularly certain versions of string theory, suggest that our three-dimensional universe might indeed be embedded in a higher dimensional space with physical significance. These extra dimensions, if they exist, could be compactified, curled up so tightly that they're undetectable at ordinary energies. Or they could be extended, with our three-dimensional universe existing as a membrane or brain within this higher dimensional bulk. In such scenarios, what lies beyond our universe could be other brains, other three-dimensional universes floating in the same higher dimensional bulk space. These parallel universes might operate according to different physical laws, contain different types of matter and energy, or exist in entirely different phases. Some speculative theories even suggest that what we call dark energy, the mysterious force accelerating the expansion of our universe, might be the result of gravitational interactions between our brain and neighboring brains in this higher dimensional space. These ideas remain highly speculative, at the frontier of theoretical physics. They emerge from mathematical models that attempt to unify quantum mechanics and general relativity, two pillars of modern physics that have proven difficult to reconcile. While mathematically elegant, these models have yet to produce testable predictions that would allow them to be verified or falsified by observation. Nevertheless, they remind us that the question of what lies beyond the universe might be more complex and more fascinating than we initially imagined. The beyond might not be a place in the conventional sense, but rather a different dimensional framework, a different geometry of space, a different regime of physical law. Returning to the more established framework of general relativity, we can ask another interesting question about the shape of space. Does it change over time? The answer is a definitive yes. According to observational evidence from distant supernovae and the cosmic microwave background, our universe is not only expanding, but accelerating in its expansion. This acceleration is attributed to dark energy, a mysterious component that makes up approximately 68% of the energy content of the universe. Dark energy acts as a kind of anti-gravity, pushing space itself apart rather than pulling matter together. As the universe expands, the shape of space evolves. If the universe is flat now, it will remain flat as it expands. If it has a slight positive curvature, this curvature will become more pronounced if the expansion were to eventually reverse and the universe collapse. If it has a slight negative curvature, this will become more pronounced as expansion continues. Current observations suggest that our universe will continue to expand forever, gradually spreading all matter thinner and thinner across ever-increasing volumes of space. Eventually, galaxies beyond our local group will recede beyond our cosmic horizon, their light unable to reach us against the tide of expanding space. In the far, far future, observers would see only a handful of nearby galaxies, with the rest of the universe having disappeared from view. This eventual isolation reminds us that the observable universe is not just spatially limited, but temporally privileged. We live in an era when we can still observe distant galaxies, still detect the cosmic microwave background, still piece together the cosmic history that brought us here. Future civilizations, emerging tens of billions of years from now, would inhabit a universe that appears much smaller, much emptier, much more finite than the one we observe today. The shape of space also influences how we think about the possibility of cosmic loops or shortcuts. In a flat, infinite universe, the only way to travel from one point to another is through the intervening space. But if space is curved or has an interesting topology, there might theoretically be shortcuts. This brings us to the concept of wormholes, hypothetical tunnels through space-time that could connect distant regions directly, bypassing the normal routes through space. Wormholes emerge as solutions to Einstein's field equations under certain conditions, but they typically require exotic forms of matter with negative energy density to remain stable and traversable. If stable wormholes could exist, they would provide a way to effectively go beyond the local region of the universe without actually crossing any boundary. You would remain within the same space-time continuum, but you would access it through a topological shortcut. Similarly, some speculative theories suggest that the extreme warping of space-time near the singularities of black holes might connect to other regions of our universe, or even to other universes entirely. These black hole bridges, sometimes called Einstein-Rosen bridges, represent another hypothetical way to access what lies beyond, without crossing a spatial boundary in the conventional sense. These ideas remain firmly in the realm of theoretical speculation. No observational evidence supports the existence of traversable wormholes or bridges between universes. The physics required to create and stabilize such structures, if possible at all, lies far beyond our current technological capabilities. Nevertheless, they highlight an important point. The question of what lies beyond the universe is not just about spatial extent, but about connectivity, about how different regions of space relate to one another, about the topology of the cosmos as well as its geometry. Another aspect of the shape of space worth considering is its homogeneity and isotropy. On the largest scales, our universe appears remarkably uniform. Matter is distributed evenly, with no special places, no centers, no edges. Space looks essentially the same in all directions and from all locations, once you average over sufficiently large volumes. This large-scale homogeneity and isotropy is known as the cosmological principle, and it forms a cornerstone of modern cosmology. It allows us to develop simplified models of the universe that capture its essential features without getting lost in local details. But the cosmological principle is an approximation valid only on scales larger than roughly 300 million light-years. On smaller scales, the universe displays rich structure: galaxies, galaxy clusters, superclusters, and the cosmic web of filaments and voids. This structure emerges from tiny quantum fluctuations in the early universe, amplified by gravity over billions of years. Could there be similar variations in the very fabric of space itself? Could the geometry or topology of the universe vary from region to region? Some speculative theories suggest that the universe might not be globally homogeneous, that distant regions beyond our observable horizon might have different properties, different physical laws, or different dimensional structures. This concept of a multiverse with varying properties challenges the cosmological principle, but emerges naturally from certain theories of cosmic inflation. If inflation produced not just our observable universe, but a vast sea of inflating space, different regions might have undergone different histories, settled into different vacuum states, and developed different physical characteristics. In such a scenario, what lies beyond our universe could be other pocket universes with their own distinct properties, separated from ours by vast expanses of inflating space. These regions would be causally disconnected from us, making direct observation impossible. But their existence might be inferred from theoretical models and perhaps subtle signatures in the cosmic microwave background. These speculations take us to the frontiers of cosmology, where established science meets theoretical possibility. They remind us that the shape of space, while seemingly abstract, has profound implications for our understanding of what exists, what can be observed, and what might lie beyond. If space is flat and infinite, as current observations suggest, then what lies beyond the observable universe is simply more universe, extending forever in all directions. If space is closed and finite, looping back on itself in higher dimensions, then there is no spatial beyond in the conventional sense, though we might speculate about the higher dimensional space in which our universe is embedded. If space has an interesting topology, connecting distant regions in unexpected ways, then what lies beyond might be accessible through cosmic shortcuts rather than conventional travel. And if space varies in its properties from region to region, then what lies beyond could be other universes with different physical laws, different dimensional structures, different possibilities for matter, energy, and perhaps even life. The shape of space determines not just how objects move within it, but what it means to go beyond it. It defines the boundary conditions of our cosmic understanding, the framework within which we ask our deepest questions about existence. As we contemplate the shape of space, we should remember that we observe it from within, as participants rather than external observers. Our measurements and observations are themselves events in space-time, subject to the same physical laws and limitations as everything else in the cosmos. This participatory perspective reminds us that the question of what lies beyond the universe is not merely academic. It touches on our place in the cosmos, our relationship to the whole of existence, our understanding of ourselves as beings embedded in a universe with a particular shape, a particular history, a particular set of possibilities. Space may be curved, but if it loops, where does it begin and where does it go? The answer may lie in dimensions we cannot directly perceive, in mathematical structures we struggle to visualize, in cosmic connections we have yet to discover. The shape of space invites us to expand not just our knowledge, but our imagination, our capacity to conceive of realities beyond our immediate experience. As we drift through the cosmos on our tiny blue planet, let us appreciate the subtle geometries that guide our journey, the invisible curvatures that shape our path, the cosmic topology that connects us to the whole. For in understanding the shape of space, we come closer to understanding our place within it, and perhaps what might lie beyond. What we see today may already be gone, and beyond them, we cannot look. Perhaps the most profound discovery in the history of cosmology came in the late 1920s, when astronomer Edwin Hubble observed that distant galaxies were moving away from us. Not just some galaxies, but virtually all of them, and not just moving away in random directions, but specifically moving outward, as if the entire cosmos were expanding uniformly in all directions. This discovery fundamentally changed our understanding of the universe. For centuries, scientists and philosophers had imagined a static cosmos, unchanging in its overall structure, but Hubble's observations revealed a dynamic universe, one that was growing larger with each passing moment. The evidence came from careful analysis of light from distant galaxies. Hubble noticed that the spectral lines in galaxy light were shifted toward the red end of the spectrum, a phenomenon known as redshift. The further away the galaxy, the greater the redshift. This pattern suggested that galaxies were receding from us at speeds proportional to their distance, a relationship now known as Hubble's law. The simplest explanation for this pattern was not that galaxies were moving through space, but that space itself was expanding, carrying galaxies along with it like raisins in rising bread dough. The galaxies themselves remain roughly the same size because the internal forces holding them together are much stronger than the effect of cosmic expansion. But the distances between galaxies grow larger over time as the fabric of space between them stretches. This expansion has been ongoing since the earliest moments after the Big Bang, the event that marked the beginning of our universe as we understand it. Initially, the universe was incredibly hot and dense, with all matter and energy compressed into a volume smaller than an atom. Then, in a fraction of a second, it began to expand and cool, eventually allowing matter to form, then atoms, then stars and galaxies. The expansion of the universe is not an explosion in space, but an expansion of space itself. This distinction is crucial for understanding what might lie beyond the universe. In an explosion, matter moves outward into pre-existing space. In cosmic expansion, space itself stretches, creating new distance between objects. If we imagine the universe as the surface of an inflating balloon, galaxies would be like dots drawn on the balloon's surface. As the balloon inflates, the dots move apart from each other, not because they're moving across the surface, but because the surface itself is expanding. Each dot sees all other dots moving away, with more distant dots receding faster. This analogy helps us understand why there appears to be no center to the cosmic expansion. From any galaxy's perspective, all other galaxies appear to be moving away. Each observer could reasonably conclude they are at the center of the expansion, but this is an illusion created by the nature of the expanding space. The rate of this expansion is described by the Hubble constant, named after Edwin Hubble. Current measurements put this value at approximately 73 kilometers per second per megaparsec. This means that for every megaparsec, roughly 3.3 million light-years, further away a galaxy is, it appears to be receding about 73 kilometers per second faster. For nearby galaxies, this recession velocity is relatively modest. The Andromeda Galaxy, our closest major galactic neighbor, is actually moving toward the Milky Way due to mutual gravitational attraction, which overcomes the effect of cosmic expansion at relatively small distances. But for distant galaxies, the recession velocity becomes enormous. Galaxies, billions of light years away, appear to be moving away from us at significant fractions of the speed of light. And herein lies a fascinating consequence of cosmic expansion. There are galaxies so distant that they appear to be receding faster than the speed of light. This doesn't violate Einstein's special relativity, because the galaxies aren't moving through space faster than light, but rather space itself is expanding between us and them. Galaxies whose recession velocity exceeds the speed of light lie beyond what's called the cosmic event horizon. Light emitted by these galaxies today will never reach us, no matter how long we wait, because the space between us is expanding too quickly. The light travels toward us at the speed of light, but new space is being created in its path faster than it can traverse. This cosmic event horizon currently lies at a distance of approximately 16 billion light-years. Any object currently beyond that distance is, in a very real sense, beyond our universe as we will ever know it. We can see some of these distant objects as they were in the past, when the universe was smaller and their light could still reach us. But we will never see what they look like today or in the future. As the universe continues to expand, and apparently at an accelerating rate, this cosmic event horizon will effectively shrink in terms of what we can potentially interact with. Galaxies that are currently visible to us will eventually cross this horizon and disappear from our potential future view. The observable universe will grow larger in terms of what we can see from the past, but smaller in terms of what we can potentially interact with in the future. This leads to a sobering thought. In the far future, trillions of years from now, astronomers in our galaxy would observe a very different cosmos than we do today. They would see only the local group of galaxies, those bound together by gravity strongly enough to overcome cosmic expansion. The rest of the universe would have disappeared beyond the cosmic horizon, their light unable to reach us against the relentless tide of expanding space. Those future astronomers might have no observational evidence of the Big Bang, no way to detect the cosmic microwave background, no ability to see the millions of galaxies we can currently observe. They might conclude they live in a small, static island universe consisting of a few nearby galaxies, unaware of the vast cosmos that once was visible. We are fortunate to live in what cosmologists call the stelliferous era, when stars still shine and the evidence of our cosmic origins is still accessible to our instruments. We inhabit a special moment in cosmic history when we can still piece together the story of the universe's birth and evolution. But the expansion of the universe raises deeper questions about what might lie beyond the cosmic horizon. If space continues beyond what we can see, how far does it extend? Is it infinite, or does it eventually loop back on itself? Does the expansion continue forever, or might it eventually slow and reverse? For decades, cosmologists assumed that the expansion of the universe should be slowing down over time due to the mutual gravitational attraction of all matter. The question was whether there was enough matter to eventually halt and reverse the expansion, leading to a big crunch, or whether the universe would expand forever, just at a gradually slowing rate. Then, in 1998, two independent teams of astronomers made a shocking discovery. By measuring the brightness and redshift of distant type Ia supernovae, stellar explosions that serve as standard candles for cosmic distance measurements, they found that the expansion of the universe was not slowing down at all. It was accelerating. Something was overcoming the gravitational attraction of matter and pushing the universe apart at an ever-increasing rate. This something was given the name dark energy, and it remains one of the greatest mysteries in modern physics. Dark energy appears to be a property of space itself. Empty space is not nothing. It contains energy, even in the absence of matter and radiation. As the universe expands, creating more space, it also creates more dark energy, which in turn causes space to expand faster, creating a feedback loop of accelerating expansion. Current observations suggest that dark energy makes up approximately 68% of the total energy content of the universe. Ordinary and dark matter together comprise only about 32%. This means the fate of the universe is determined primarily by dark energy, not by matter. If dark energy maintains its current properties, the universe will continue to expand forever, at an ever-accelerating rate. Eventually, all galaxies beyond our local gravitationally bound group will disappear from view. But dark energy remains poorly understood. We don't know whether its density will remain constant as the universe expands, increase, or perhaps even decrease. Different behaviors would lead to different cosmic fates, from eternal expansion to potential recollapse, or even more exotic scenarios. Some theoretical models suggest that dark energy might be related to the vacuum energy of quantum fields, the same energy that causes the Casimir effect, a measurable force between closely spaced metal plates in a vacuum. But when physicists calculate how much vacuum energy should exist according to quantum field theory, they get a value that's larger than the observed dark energy by a factor of about 10 to the power of 120, one of the most extreme disagreements between theory and observation in all of science. Other models propose that dark energy might be a new type of dynamical energy field called quintessence, which could vary over time and space. Or it might be a sign that Einstein's theory of general relativity needs modification at the largest scales. Or it could be something even more exotic that we have yet to imagine. The nature of dark energy has profound implications for what might exist beyond our observable universe. If dark energy is indeed a property of space itself, then it should exist throughout the entire cosmos. not just the part we can see. An infinite universe filled with dark energy would expand forever, creating an ever-growing gulf between gravitationally bound structures. But if dark energy is a field that varies across space, or if it's a misunderstanding of gravity, then different regions of the universe beyond our horizon might behave differently. Some might expand faster, others slower. Some might eventually recollapse, while others continue to expand. This brings us to another fascinating possibility. What if the accelerating expansion we observe is just a local phenomenon? What if our observable universe is just one bubble in a much larger cosmos, with different regions experiencing different expansion rates, or even different physical laws? This concept emerges naturally from certain theories of cosmic inflation, which suggest that the exponential expansion in the earliest moments after the Big Bang didn't end everywhere at once. It might have ended in our region, allowing matter to form and galaxies to evolve, while continuing elsewhere, creating a vast sea of still inflating space with occasional bubbles, where inflation has stopped and matter has formed. In such a scenario, our observable universe would be just one bubble among many, each potentially with its own version of the Big Bang, its own cosmic history, perhaps even its own physical constants or laws. What lies beyond our universe might be other universe bubbles, separated from ours by regions of rapidly inflating space. These bubbles would be effectively causally disconnected from one another. No signal, no light, no information of any kind could travel from one bubble to another through the inflating space between them. They would be, for all practical purposes, separate universes, even though they're all part of the same underlying cosmic structure. This multiverse concept, while speculative, has emerged independently from several different approaches to theoretical physics, including inflation theory, string theory, and quantum mechanics. It suggests that what lies beyond our observable universe might not just be more of the same, but regions with fundamentally different properties. But returning to what we can actually observe, the expansion of the universe has another important implication for our understanding of cosmic history and what might lie beyond. The fact that the universe is expanding today means it was smaller in the past. Tracing this expansion backward in time leads to the conclusion that the entire observable universe was once compressed into an extremely hot, dense state, the Big Bang singularity. Prior to the development of Big Bang cosmology, many scientists supported the steady state theory, which held that the universe had always existed in roughly its present form, with new matter continuously created to fill the gaps created by expansion. But the discovery of the cosmic microwave background radiation in 1965, along with the observed abundance of light elements like hydrogen and helium, provided strong evidence for the Big Bang model. The Big Bang represents not just the beginning of matter and energy as we know them, but the beginning of space and time themselves. According to our current understanding of physics, it makes no sense to ask what happened before the Big Bang, because time itself began at that moment. Similarly, it makes no sense to ask what exists outside the universe if the universe contains all of space. And yet, these questions persist, pulling at our minds, challenging our understanding. Modern physics provides some tentative approaches to these seemingly unanswerable questions. Some speculative models suggest that our Big Bang might have emerged from a quantum fluctuation in a pre-existing state, or from the collapse of a previous cosmic cycle, or from a higher dimensional bulk space, or from any number of exotic possibilities at the frontier of theoretical physics. These models remain highly speculative, beyond our current ability to test observationally. They remind us that the boundary between science and philosophy becomes blurry at the edges of our understanding, where mathematical consistency and theoretical elegance must temporarily stand in for empirical validation. The expansion of the universe also raises interesting questions about the nature of infinity. If the universe is infinite now, it must have been infinite at the moment of the Big Bang as well, just with everything infinitely close together. An infinite universe doesn't expand into anything. It simply becomes less dense as space stretches. But if the universe is finite, with a definite volume and a definite amount of matter and energy, then its boundary is not a physical edge, but a geometric closure, like the surface of a sphere, which has finite area but no boundary. Such a universe would still not expand into anything. It would simply increase in volume, while maintaining its closed topology. The expansion of the universe, particularly its acceleration, challenges our intuitive notions of gravity as a purely attractive force. On the largest scales, the universe appears to be dominated by a form of anti-gravity, pushing space apart rather than pulling matter together. This raises the possibility that what we call gravity might be more complex, more multifaceted than we previously understood. Some theoretical approaches to quantum gravity, attempts to reconcile general relativity with quantum mechanics, suggest that gravity might leak into extra dimensions, or emerge from deeper underlying principles, or connect our universe to others through wormholes or other exotic space-time structures. These speculations bring us back to our central question: is there something beyond the universe? The expansion of space, particularly accelerating expansion, suggests possibilities that would have seemed like pure fantasy a century ago. The universe might be just one bubble in a vast multiverse. It might be one brain among many in a higher dimensional bulk space. It might be one cycle in an eternal sequence of expansions and contractions. Or it might be all there is, infinite and complete, with nothing beyond because there is no beyond, no outside, no exterior to all that exists. The accelerating expansion of the universe reminds us that the cosmos is not static but dynamic, not fixed but evolving, not eternal in its present form but changing over timescales that dwarf human experience. What we see today in our telescopes is not just spatially distant, but temporally remote, a glimpse of the universe as it was millions or billions of years ago. Some of those distant galaxies have already disappeared beyond our cosmic horizon, their future light unable to reach us against the tide of expanding space. What we see today may already be gone, and beyond them we cannot look. Yet in this cosmic transience, in this fleeting glimpse of a universe in motion, we find both limitation and possibility. We cannot see beyond the cosmic horizon, but we can imagine, theorize, calculate, and wonder. We can trace the trajectories of expanding space and follow them, if not with our instruments, then with our mathematics, our physics, our cosmology, and perhaps most importantly, our curiosity. The expansion of the universe is not just a physical process, but an invitation to expand our thinking, to stretch our understanding as space itself stretches, to grow our knowledge as the cosmos grows, to accelerate our inquiry as the expansion accelerates. In exploring what might lie beyond the observable universe, we push against the boundaries of knowledge itself, expanding our intellectual horizon even as the cosmic horizon recedes from view. If the universe has no edge, then there is nothing to go beyond. And yet, we ask, we have explored the observable universe, that spherical volume of space and time whose light has had the opportunity to reach us during the 13.8 billion years since the Big Bang. We have examined the shape of space and considered how it expands. Now we face perhaps the most profound question of all. Does space extend forever? Is there an infinite cosmos beyond our cosmic horizon, or does the universe somehow end? This question takes us to the frontier of cosmology, where observation meets theory, where physics meets philosophy, where knowledge meets speculation. It is a question that has fascinated humanity since we first gazed at the night sky and wondered about our place in the cosmos. Modern cosmology offers several possibilities for what might exist beyond the observable universe. Let us consider each in turn, weighing the evidence, exploring the implications, and always remembering the limits of our knowledge. The simplest possibility is that the universe extends infinitely in all directions, filled with galaxies, stars, planets, and perhaps life, stretching endlessly beyond our cosmic horizon. In this scenario, what lies beyond the observable universe is simply more of the same: more galaxies, more clusters, more cosmic web, all obeying the same physical laws we observe in our cosmic neighborhood. This infinite universe would not be exactly the same everywhere. The distribution of matter would vary from region to region, creating different patterns of galaxies, different arrangements of stars, different planetary systems. But on the largest scales, averaged over sufficiently large volumes, it would appear roughly homogeneous, with the same average density of matter and energy throughout its infinite expanse. An infinite universe has some mind-bending implications. With an unlimited canvas and a finite set of possible arrangements of matter, every possible configuration would not only exist, but would exist an infinite number of times. There would be an infinite number of regions exactly like our observable universe, containing galaxies identical to the Milky Way, planets identical to Earth, and beings identical to each of us, living out the same lives or slightly different variants. This concept, sometimes called the infinite monkey theorem in a more limited context, follows naturally from the combination of infinity and probability. In an infinite universe, with a non-zero probability for any particular arrangement of matter, that arrangement must occur somewhere, and indeed must occur infinitely many times. But infinity is a challenging concept, both mathematically and philosophically. An infinite universe raises questions about countability, about the meaning of everything, about whether infinity is a physical reality or merely a mathematical abstraction. Some physicists suggest that true infinity might not exist in the physical world, that what appears infinite might actually be merely extremely large. How could we determine whether the universe is truly infinite? Direct observation cannot settle the question, as we can only see the finite volume of the observable universe. But we can look for clues in the geometry of space. As we discussed earlier, current observations from the cosmic microwave background and other sources indicate that our universe is remarkably flat, with any curvature being so slight as to be nearly undetectable with current methods. A perfectly flat universe that is simply connected, meaning it doesn't loop back on itself in some higher dimension, would indeed be infinite. But flatness alone doesn't guarantee infinity. The universe could be flat yet finite if it has an interesting topology like a three-dimensional torus or another more exotic shape. In such a case, traveling far enough in one direction would eventually bring you back to your starting point, not because space curves, but because it connects to itself in unexpected ways. Astronomers have searched for evidence of such a wrapped universe by looking for repeating patterns in the cosmic microwave background or in the distribution of galaxies. If we could see all the way around the universe, we would observe the same structures from different angles. So far, no compelling evidence for such repetition has been found, suggesting that if the universe does wrap around, it does so on a scale larger than the observable universe. Another possibility is that the universe is nearly flat, but has a slight positive curvature too small to be detected with current instruments. In this scenario, the universe would be finite but boundless, like the surface of a sphere, but in 3 dimensions. It would contain a finite volume of space and a finite amount of matter, yet it would have no edge or boundary. If you could travel far enough in one direction in such a universe, you would eventually return to your starting point, having circumnavigated the entire cosmos. The total volume would be enormous, but not infinite. What lies beyond the universe in this case? Nothing, because there is no beyond. The universe loops back on itself without any boundary to cross. Alternatively, the universe might have a slight negative curvature, like a saddle shape. A negatively curved universe would also extend infinitely if it is simply connected. Space would continue forever in all directions, expanding ever more rapidly as you travel outward. Current observations slightly favor a flat or very slightly positively curved universe, but the margin of error in these measurements leaves all possibilities open. The universe might be exactly flat, or it might curve so gently that we cannot yet detect the curvature across the limited volume we can observe. Beyond these relatively conservative possibilities lie more speculative ideas that emerge from theories of cosmic inflation, the period of exponential expansion thought to have occurred in the first fraction of a second after the Big Bang. Inflation theory, first proposed by physicist Alan Guth in the early 1980s, elegantly explains several puzzling features of our universe, including its flatness, homogeneity, and the specific pattern of fluctuations seen in the cosmic microwave background. But inflation also suggests that our observable universe might be just one bubble in a much larger, perhaps infinite sea of inflating space. According to some versions of inflation theory, particularly eternal inflation, the process that caused our universe to expand exponentially in its earliest moments continues in other regions beyond our cosmic horizon. Occasionally, a region stops inflating and becomes a bubble universe like our own, where normal matter can form and evolve. But between these bubbles, space continues to inflate, doubling in size in a tiny fraction of a second, continuously creating more volume than all the bubble universes combined. In this scenario, what lies beyond our observable universe would be, initially, more of the same, a continuation of our bubble. But beyond that would lie the still inflating space that separates our bubble from others, and beyond that, other bubble universes with potentially different properties. These other bubble universes might have different initial conditions, different patterns of matter distribution, or even different physical constants or laws. Some might be suitable for life, others completely inhospitable. Some might collapse almost immediately, others expand forever. The collection of all these bubble universes is sometimes called the multiverse. The multiverse concept raises profound questions about uniqueness, probability, and the nature of physical law. If there are countless other universes with different properties, why does our universe have the specific characteristics it does? Is there a deeper principle that determines the range of possible universes, or is it simply random variation? Some theorists suggest that the apparent fine-tuning of our universe for the existence of complex structures and eventually life might be explained by the multiverse. With enough different universes, each with random variations in their physical parameters, eventually one would have the right conditions for beings like us to evolve and ask these questions. This is known as the anthropic principle. We observe a universe suitable for our existence because we could only exist in such a universe to make the observation. Critics argue that the multiverse hypothesis, particularly in its more extravagant forms, stretches the definition of science because it posits the existence of regions that are in principle unobservable. If we can never detect these other universes or measure their properties, is the multiverse a scientific theory or merely a philosophical speculation? Proponents counter that the multiverse emerges naturally from well-established theories like inflation, and that even if we cannot directly observe other universes, we might find indirect evidence for their existence. For example, if our universe collided with another bubble universe in the past, it might have left detectable signatures in the cosmic microwave background. Beyond inflation theory, other approaches to fundamental physics also suggest the possibility of multiple universes or dimensions beyond our own. String theory, a candidate for a unified theory of all forces including gravity, typically requires extraspatial dimensions beyond the three we experience. These additional dimensions might be compactified, curled up so tightly they're undetectable at ordinary energies, or they might be extended, with our three-dimensional universe existing as a membrane or brane within this higher dimensional space. In some string theory scenarios, other branes might exist parallel to our own, perhaps separated by only a tiny distance in a fourth spatial dimension. These branes could have their own matter, energy, and even different physical laws. Gravity, being a distortion of space-time itself, might leak between branes, potentially allowing for indirect detection of neighboring universes through gravitational effects. Another framework that suggests the existence of multiple universes comes from quantum mechanics, particularly the many worlds interpretation, first proposed by Hugh Everett in the 1950s. According to this interpretation, every quantum measurement splits reality into multiple branches, each representing a different outcome. In effect, all possibilities occur, just in different branches of an ever-multiplying wave function. If the many worlds interpretation is correct, then what lies beyond our universe would be these other branches of reality, these other worlds where history took different turns at each quantum fork in the road. Every decision you've ever made, every coin you've ever flipped, every quantum particle that could have gone one way or another, all possibilities would exist in different branches of the universal wave function. These various multiverse concepts, inflationary, string theoretic, quantum, are not necessarily mutually exclusive. Reality might be even stranger than any one of these theories suggests, incorporating elements of each or perhaps something entirely different that we have yet to imagine. But let us step back from these speculative frontiers and return to what we can observe and measure. Even if the universe is infinite, not everything is possible. The laws of physics, whatever their ultimate form, constrain what can exist. An infinite universe doesn't mean that somewhere there's a planet made entirely of gold, or a region where gravity repels rather than attracts, or a galaxy where the speed of light is different. The infinity of the universe, if it is indeed infinite, would be an infinity of variations within the constraints of physical law, not an infinity of arbitrary possibilities. Think of it like an infinite series of numbers. The sequence 2, 4, 6, 8 continues forever, but it will never include the number 3. What might these endless variations look like? They would include galaxies with slightly different arrangements of stars, planets with different compositions and atmospheric conditions, perhaps life forms adapted to environments we can barely imagine. They would include regions where cosmic evolution took slightly different paths, where galaxies formed earlier or later, where star formation proceeded at different rates. But the fundamental particles, forces, and physical constants would likely remain the same throughout an infinite cosmos, at least within our bubble universe. The electron would have the same mass, the gravitational constant the same value, the speed of light the same limit. The possibility that physical constants might vary across vast cosmic distances remains an active area of research. Some theories suggest that what we call constants might actually be fields that can take different values in different regions of space or different eras of cosmic history. Observations of extremely distant quasars have been used to search for any variation in the fine structure constant, which governs electromagnetic interactions. But so far, no definitive evidence for such variation has been found. If the universe does extend infinitely, then there's an important distinction to make between the physical infinity of space and the practical limitations of what we can ever observe or influence. Due to the accelerating expansion of the universe, there is a cosmic event horizon beyond which we can never send or receive signals, no matter how long we wait. This horizon currently lies at a distance of approximately 16 billion light-years. Any object currently beyond that distance is forever beyond our reach. We can see some of these distant objects as they were in the past, when the universe was smaller and their light could still reach us. But we will never see what they look like today or in the future, and we can never send a signal that would reach them. This means that, even if the universe is infinite, the portion with which we can ever interact is finite. There is an absolute limit to what we can observe, what we can influence, what we can ever know through direct measurement. Beyond that boundary lies what might be called the unobservable universe, regions that exist, but with which we can never have causal contact. This cosmic event horizon is not fixed, but shrinks over time as the universe's expansion accelerates. Eventually, in the far future, all galaxies beyond our local gravitationally bound group will disappear from view, their light unable to overcome the ever-widening gulf of expanding space. Future civilizations arising in our galaxy, trillions of years from now, would observe a very different cosmos than we do, with much of the universe having receded beyond the horizon of visibility. This eventual isolation reminds us that our current era is cosmologically special. We live at a time when we can still observe distant galaxies, still detect the cosmic microwave background, still piece together the history of the universe from the light of ancient objects. We are fortunate to inhabit what has been called the cosmic Middle Ages, when the universe is mature enough for complex structures like us to exist, yet young enough for the evidence of cosmic origins to remain accessible. But whether the universe is finite or infinite, whether space has a boundary or extends forever, one thing seems certain: there is vastly more to the cosmos than we can currently observe. The observable universe, enormous as it is, represents at most a tiny fraction of all that exists. This humbling realization doesn't diminish the importance of our observations or the power of our theories. Rather, it places them in context, reminding us that our knowledge, impressive as it is, remains limited and provisional. The universe or multiverse may be stranger and more wonderful than our current understanding suggests. The question of whether space extends forever also has philosophical implications. If the universe is truly infinite, containing endless variations of cosmic structure, what does that mean for concepts like uniqueness or significance? Does infinity make everything simultaneously special and ordinary? Some find the idea of an infinite universe unsettling, suggesting it might render our existence meaningless amid countless identical copies. Others find it awe-inspiring, a cosmic canvas vast enough to contain all possibilities, all stories, all forms of beauty and complexity that the laws of physics allow. Perhaps the most profound aspect of this question is how it connects abstract mathematics to physical reality. Infinity is a mathematical concept, one that has proven useful in developing the equations that describe our universe. But does mathematical infinity correspond to physical infinity? Does the universe actually contain an infinite number of galaxies, an infinite amount of matter, an infinite expanse of space? Or is infinity merely a convenient approximation, a way of describing something merely unimaginably vast? The ancient Greeks distinguished between potential infinity and actual infinity. Potential infinity is the possibility of always adding one more, of always going further, of never reaching an end. Actual infinity is the completed totality, the entire infinite set considered as a single entity. Modern mathematics accepts actual infinity, but some physicists question whether physical reality does the same. There might be fundamental limits to space, time, and complexity embedded in the deepest laws of physics. Quantum gravity, the still developing theory that seeks to reconcile general relativity with quantum mechanics, suggests the possibility of a smallest meaningful length, the Planck length, and a smallest meaningful time, the Planck time. If space and time are ultimately quantized, built from discrete units rather than infinitely divisible, then perhaps the universe itself is finite rather than infinite, though still unimaginably vast. These questions remain open, at the frontier of physics and cosmology. S. Haldane. The cosmos may contain depths of complexity and subtlety that our evolved primate brains, adapted for life on the African savanna, struggle to comprehend. And yet, remarkably, we can ask these questions. We can develop mathematical models of cosmic inflation, calculate the curvature of space-time, measure the expansion rate of the universe, and peer back in time to nearly the beginning of everything we know. Our capacity for abstract thought, for scientific inquiry, for wonder and curiosity about our cosmic context seems almost miraculous, given our humble evolutionary origins. If the universe has no edge, then there is nothing to go beyond, at least not in the spatial sense. An infinite universe would not be contained within anything larger. It would simply be extending endlessly in all directions. The concept of beyond would lose its spatial meaning, though it might retain meaning in other dimensions or frameworks. But if the universe does have a boundary, whether a geometric closure like a hypersphere or a more exotic topology, then the question of what lies beyond becomes even more perplexing. Does anything exist outside the universe? Is there a metaspace in which our universe is embedded? Is there something beyond space itself? These questions push against the limits of science, approaching realms traditionally explored by philosophy and theology. They remind us that while science has made remarkable progress in understanding the cosmos, there remain mysteries at the boundary of knowledge, puzzles that may require new frameworks, new mathematics, new concepts we have yet to develop. Perhaps most remarkably, despite the vastness of the cosmos and our limited vantage point within it, we continue to ask these questions, to develop theories, to make observations, to push the boundaries of knowledge outward. We may never know with certainty whether the universe is finite or infinite, whether space extends forever or loops back on itself, whether there are other universes beyond our own. But in asking these questions, in contemplating the cosmic scale, we participate in one of humanity's most noble endeavors, the quest to understand our place in the cosmos, to comprehend the nature of reality itself. Beyond the observable universe lies either more universe, perhaps infinitely more, or a boundary that defines the limits of space itself. Either possibility stretches our understanding, challenges our intuition, and invites us to expand our cosmic perspective. Whether space goes on forever or eventually curves back on itself, the journey of exploration, of discovery, of wonder at the vast cosmos we inhabit continues. And perhaps that's the most profound answer to our question. Beyond the universe as we currently understand it, lies more understanding to be gained, more discoveries to be made, more wonder to be experienced. The horizon of knowledge expands as we approach it, revealing new vistas, new questions, new mysteries to contemplate. If the universe has no edge, then there is nothing to go beyond. And yet, we ask. In that asking, in that reaching beyond what we know, we find something quintessentially human: curiosity, wonder, the desire to understand. Whatever lies beyond the universe, the act of questioning itself, connects us to the cosmos in a profound and meaningful way. If our universe is a bubble, what else floats in the dark beyond? Throughout human history, we have consistently discovered that what we thought was everything is merely a part of something larger. Ancient peoples believed the Earth was all that existed, with the heavens as a dome overhead. Later, we realized Earth is one planet among several orbiting the Sun. Then we discovered that our Sun is one star among hundreds of billions in the Milky Way galaxy. And eventually, we learned that the Milky Way is just one galaxy among trillions in the observable universe. Could this progression continue? Could our entire universe, vast as it is with its hundreds of billions of galaxies stretching across billions of light years, be just one universe among many in a greater multiverse? This is not merely philosophical speculation. The concept of a multiverse emerges naturally from several well-established theories in modern physics. While we cannot directly observe other universes, the mathematics that successfully describes our universe often points to their existence. Let us explore the different types of multiverses that contemporary physics suggests might exist beyond our cosmic horizon. The first, and perhaps most straightforward type of multiverse, comes from cosmic inflation theory. As we've discussed earlier, inflation was an extremely rapid expansion of space that occurred in the first fraction of a second after the Big Bang. This theory, first proposed by physicist Alan Guth in 1980, elegantly explains several observed features of our universe, including its remarkable flatness and the specific pattern of temperature fluctuations in the cosmic microwave background radiation. But in many versions of inflation theory, particularly eternal inflation, developed by Andrei Linde, Alexander Vilenkin, and others, the inflationary process never completely stops. While inflation ended in our region of space, allowing normal matter to form and galaxies to evolve, it continues elsewhere, with space expanding at an exponential rate, doubling in size in a minuscule fraction of a second. In this eternally inflating space, occasional regions stop inflating and become bubble universes like our own. These bubbles appear when random quantum fluctuations cause a small patch of inflating space to decay into a lower energy state, triggering a local Big Bang. Our entire observable universe would be just one such bubble in this picture, with countless others continually forming in the ever-expanding sea of inflating space. These other bubble universes would be separated from ours by regions of still inflating space, expanding so rapidly that no signal or influence could ever pass between bubbles. Each bubble would be, for all practical purposes, a separate universe, with its own beginning, its own timeline, and potentially its own set of physical laws. In this inflationary multiverse, what lies beyond our universe would be first the continuation of our own bubble beyond our observable horizon, and then the inflating space that separates our bubble from others, and beyond that, other bubble universes with potentially different properties. Would these other universes be exactly like ours? Not necessarily. The process that determines the fundamental constants of nature might involve random quantum fluctuations leading to different values in different bubble universes. Some bubbles might have stronger gravity, others a different balance between fundamental forces, others different types of elementary particles. String theory is a candidate for the fundamental theory of physics, unifying all forces, including gravity, into a single mathematical framework. One of its most surprising features is that it doesn't provide a unique solution for the universe. Instead, it suggests a vast landscape of possible vacuum states, perhaps 10 to the power of 500 or more, each corresponding to a different set of physical laws. In string theory, our universe would occupy just one valley in this vast landscape of possibilities. Other regions of the multiverse would have different vacuum states, different physical constants, different numbers of effective dimensions, even different types of elementary particles. Some might permit complex chemistry and potentially life, while others might be completely inhospitable to any form of complexity. The string theory landscape connects naturally with eternal inflation, providing a mechanism for different bubble universes to settle into different vacuum states. Together, they suggest a multiverse of staggering diversity, containing almost every possible variation of physical law permitted by the underlying mathematics of string theory. This enormous variety leads to a controversial but intriguing explanation for a long-standing puzzle in physics: Why do the fundamental constants of our universe appear to be fine-tuned for the existence of life? Constants like the strength of gravity, the mass of the electron, and the strength of the nuclear forces all seem calibrated with remarkable precision to allow for stable atoms, long-lived stars, and the chemistry needed for biology. If the multiverse contains every possible combination of these constants, then intelligent observers would naturally find themselves in the rare universes suitable for their evolution. This application of what's called the anthropic principle doesn't explain why the constants have the values they do in an absolute sense, but it explains why we observe these particular values. We couldn't exist in a universe with substantially different constants. Critics argue that this anthropic reasoning is unscientific because it cannot be tested and doesn't provide the kind of deterministic explanation traditionally sought in physics. Defenders respond that in a sufficiently diverse multiverse, anthropic selection becomes an unavoidable part of our understanding, similar to how evolutionary selection explains biological adaptations. A third type of multiverse emerges from quantum mechanics, specifically the many worlds interpretation first proposed by Hugh Everett in 1957. According to this interpretation, every time a quantum event could have multiple outcomes, the universe splits into multiple branches, each representing a different outcome. For example, when an electron passes through a double slit and could be detected at various positions on a screen, the many worlds interpretation suggests that the universe branches into multiple realities, with the electron appearing at a different position in each. Similarly, every decision you make, every random event in history, every quantum fluctuation in the early universe would create new branches. In this quantum multiverse, what lies beyond our universe would be these other branches of reality, effectively other universes where history took different turns at each quantum decision point. These branches would not exist in physical space beyond our universe, but in a higher dimensional configuration space, a mathematical structure called Hilbert space that encompasses all possible quantum states. While the many worlds interpretation remains controversial among physicists, it has gained significant support because it takes quantum mathematics at face value without adding the mysterious collapse of the wave function found in more traditional interpretations. If correct, it suggests a multiverse of almost unimaginable complexity, containing every possible version of cosmic and human history permitted by quantum mechanics. A fourth type of multiverse comes from brane theory, an offshoot of string theory. In this framework, our three-dimensional universe exists as a membrane or brane floating in a higher dimensional space. Other branes might exist parallel to our own, perhaps separated by only a tiny distance in a fourth spatial dimension, each with its own matter and energy. Gravity, being a distortion of space-time itself, might leak between these branes, potentially allowing for indirect detection of neighboring universes through gravitational effects. Some speculative theories suggest that what we call dark energy, the mysterious force accelerating the expansion of our universe, might result from gravitational interactions with neighboring branes. In the brane multiverse, what lies beyond our universe would be these other branes, these parallel universes existing alongside our own in higher dimensions. They would not be located in our three-dimensional space, but would exist in dimensions we cannot directly perceive. Beyond these four relatively well-developed multiverse concepts, inflationary, landscape, many worlds, and brane, physicists have proposed other, more speculative possibilities. Some suggest that each black hole in our universe might give birth to a new universe through a process similar to inflation, with the parameters of the new universe slightly altered from its parent. Others propose cyclic models where our universe represents just one cycle in an infinite sequence of expansions and contractions, with different physical properties in each cycle. The sheer variety of multiverse concepts might seem overwhelming, and indeed, some physicists criticize the entire multiverse framework as overly speculative, unfalsifiable, and therefore outside the bounds of proper science. Others argue that we shouldn't mistake a limitation in our ability to observe for a fundamental limit on reality itself. If our best theories predict the existence of other universes, they suggest, we should take that prediction seriously, even if direct observation remains impossible. This tension between theoretical prediction and observational verification lies at the heart of the multiverse debate. Science traditionally progresses through the interplay of theory and observation, with theories making predictions that can be tested through experiment or observation. But if the multiverse exists, most parts of it lie fundamentally beyond our observational reach. Are there any ways we might find evidence for the multiverse, even indirectly? Several possibilities have been suggested. If our universe collided with another bubble universe in the past, it might have left detectable patterns in the cosmic microwave background radiation. Certain features of our universe, such as its nearly flat geometry or the specific spectrum of density fluctuations, might be better explained by multiverse models than by single universe alternatives. Some theorists have suggested that the parameters of our universe might show signs of optimization for the production of black holes, which could make sense if black holes spawn new universes. Others propose that certain quantum gravity effects might allow for information transfer between universes under special circumstances, potentially leaving subtle but detectable signatures. So far, no compelling observational evidence for the multiverse has been found, but the search continues, with cosmologists developing ever more sophisticated methods and instruments to probe the earliest moments of our universe, when any connection to a broader multiverse might be most apparent. Beyond the scientific questions, the multiverse concept raises profound philosophical implications. If the multiverse contains every possible variation of physical law, every possible cosmic history, every possible arrangement of matter and energy, what does that mean for concepts like uniqueness, purpose, or significance? Some find the multiverse unsettling, suggesting it might render our existence arbitrary or meaningless amid countless variations. Others find it awe-inspiring, a framework vast enough to contain all possibilities, all forms of complexity, all versions of cosmic evolution that the underlying mathematics allows. The multiverse also intersects with ancient philosophical questions about necessity and contingency. Are the laws of physics as we observe them necessary, the only logically possible set? Or are they contingent, just one possibility among many? The multiverse suggests the latter, that the specific details of our universe, the exact values of fundamental constants, the particular types of particles, the four fundamental forces, are not uniquely determined by some deep principle, but are essentially random selections from a vast landscape of possibilities. This randomness is constrained, however, by the underlying mathematical structure of the multiverse, whether from string theory, quantum mechanics, or some deeper theory yet to be discovered. Not everything is possible, even in the multiverse. There would still be patterns, principles, constraints on what can exist, even if these operate at a meta level above the laws of any individual universe. The multiverse concept also challenges our intuitions about infinity. An infinite multiverse would contain infinite variations, infinite copies of everything that can exist, infinite versions of cosmic and human history. Even in an infinite multiverse, there would be constraints on what's physically possible, patterns that emerge from the underlying mathematics. Perhaps the most profound aspect of the multiverse concept is how it continues a historical trend of discoveries that repeatedly expand our cosmic perspective. The Copernican revolution displaced Earth from the center of the cosmos. The discovery of galaxies beyond the Milky Way showed that our galaxy is just one among billions. The multiverse would extend this progression, suggesting that our entire universe, with its hundreds of billions of galaxies, might be just one among countless others. Each of these perspective shifts has been challenging, even threatening, to the prevailing worldview of its time. Each has required us to reimagine our place in the cosmos, to find meaning and significance in a larger, less human-centered framework. The multiverse represents a similar challenge, inviting us to expand our cosmic perspective beyond the bounds of our single universe. If the multiverse exists, what might these other universes be like? The answer depends on which type of multiverse we're considering and how much variation is possible in the fundamental laws. In the inflationary multiverse, other bubble universes might have the same basic physical laws as ours, but different initial conditions, leading to different patterns of galaxy formation, different distributions of matter and energy, perhaps different balances between ordinary matter, and dark energy. In the string theory landscape, the differences could be more profound. Some universes might have different types of elementary particles, different numbers of effective dimensions, different strengths of fundamental forces. Some might lack stable atoms, making chemistry and conventional life impossible. Others might have more complex chemistry than our own, allowing for forms of organization we can barely imagine. In the many worlds quantum multiverse, the variations would include every possible outcome of every quantum event in cosmic history. There would be universes nearly identical to our own, except for the position of a single electron, and others radically different because of quantum fluctuations in the early universe that led to different patterns of cosmic structure. In the brane multiverse, other universes might occupy the same higher dimensional space as our own, perhaps with their own versions of fundamental particles and forces, their own cosmic histories, their own possibilities for complexity, and perhaps consciousness. These different conceptions of the multiverse are not necessarily mutually exclusive. Reality might incorporate elements of several or all of these frameworks, or perhaps something even more exotic that we have yet to imagine. The multiverse might be more complex, more varied, more multi-layered than any single theory currently suggests. But we should be careful not to treat the multiverse as a catch-all explanation for anything we don't understand. While it provides a framework for thinking about certain puzzles in cosmology and fundamental physics, it's not a substitute for careful observation, precise mathematics, and rigorous testing of hypotheses. The multiverse remains a theoretical concept, one that emerges from our best physical theories but still awaits confirming evidence. We should also distinguish between different levels of confidence in multiverse theories. The extension of our universe beyond the observable cosmic horizon is supported by strong theoretical and observational evidence, including the observed homogeneity and isotropy of the cosmos. The inflationary multiverse follows naturally from well-established inflationary theory, which successfully explains several observed features of our universe. The string theory landscape and brane multiverse concepts depend on string theory, which remains a work in progress, mathematically elegant but still lacking clear experimental confirmation. The many worlds interpretation of quantum mechanics depends on a particular interpretation of quantum theory, one that has strong advocates but is not universally accepted among physicists. These distinctions matter. When we ask what lies beyond our universe, we should be clear about the level of certainty or speculation involved in different answers. Some multiverse concepts are closely tied to well-established physics, while others remain more speculative, at the frontier of theoretical exploration. What unites all these multiverse concepts is a common suggestion: that reality is larger, more diverse, more multifaceted than the universe we can observe, that our cosmic horizon, vast as it is, encompasses only a tiny fraction of all that exists, that the story of the cosmos is grander, more complex, more surprising than we had imagined. If our universe is a bubble, what else floats in the dark beyond? Perhaps other bubbles, other universes, other realms of physical law and cosmic possibility. Perhaps a landscape of different vacuum states, each with its own physics, its own chemistry, its own potential for complexity. Perhaps parallel branes, shadow worlds existing alongside our own in higher dimensions. Perhaps the countless branches of a quantum wave function containing every possible cosmic history allowed by quantum mechanics. Or perhaps something else entirely, something we have yet to conceive, something beyond our current mathematics, beyond our present theories, beyond our existing conceptual frameworks. The history of cosmology suggests humility about the limits of our current understanding. Each major advance has revealed the cosmos to be stranger, more wonderful, more surprising than we had previously imagined. The multiverse hypothesis invites us to continue this journey of cosmic discovery, to push beyond the boundaries of our observable universe, to contemplate the possibility that reality is even grander than we currently envision. S. Haldane. And yet, remarkably, we can imagine it, or at least begin to. We can develop mathematical models, formulate theories, propose mechanisms for how a multiverse might operate. We can make tentative predictions, suggest possible observations, design instruments and experiments to probe the earliest moments of our universe for hints of what might lie beyond. This capacity for abstract thought, for mathematical reasoning, for cosmic imagination seems almost miraculous given our evolutionary origins as savanna-dwelling primates. Yet here we are, contemplating not just our planet or our galaxy or our universe, but the entire multiverse, the full scope of physical reality as our best theories currently suggest it. Perhaps this is the greatest wonder of all, that beings like us, composed of the same atoms and molecules as the rest of the cosmos, governed by the same physical laws emerging through the same evolutionary processes, can develop the conceptual tools to comprehend the universe and even contemplate what might lie beyond it. The multiverse hypothesis reminds us that our cosmic exploration is far from complete, that the horizon of understanding continues to recede as we approach it, revealing new vistas, new questions, new mysteries to contemplate. It suggests that beyond our universe, beyond everything we can currently observe, existence continues, reality unfolds. The cosmic story extends into dimensions and possibilities we are only beginning to glimpse. Whether the multiverse exists in physical reality or merely as a mathematical possibility, it expands our cosmic perspective, challenges us to think beyond the confines of our observable universe, invites us to consider the true extent of physical reality. In contemplating the multiverse, we participate in one of humanity's most noble endeavors, the quest to understand our place in the cosmos, to comprehend the nature of reality itself, to expand our vision beyond the immediately observable to the full tapestry of existence. If our universe is a bubble, what else floats in the dark beyond? We may never know with certainty, but in asking the question, in developing the mathematics, in proposing the theories, in designing the observations, we reach beyond our cosmic horizon, beyond the limits of our current knowledge, toward a deeper understanding of the ultimate nature of reality. Some edges are not physical, they are limits of knowing. Throughout our journey so far, we've explored the observable universe, the shape of space, cosmic expansion, and various multiverse theories. But underlying all these discussions is a profound question. What can we actually know about what lies beyond our cosmic horizon? What are the fundamental limits to observation, and how do they shape our understanding of the universe and what might lie beyond it? To understand these limits, we must first recognize that all our knowledge of the cosmos comes through observation, the detection of light, gravitational waves, neutrinos, and cosmic rays that reach Earth from distant regions of space. These messengers carry information across the vast cosmic distances, allowing us to study objects and events we can never visit directly. But there are fundamental physical boundaries to what we can observe, boundaries set not by the limitations of our technology, but by the laws of physics themselves. Let us explore these observational horizons and what they tell us about the limits of cosmic knowledge. The most basic observational limit is the particle horizon, which defines the boundary of the observable universe. As we've discussed previously, this horizon exists because the universe has a finite age, approximately 13.8 billion years, and light travels at a finite speed. We cannot see objects whose light hasn't had time to reach us since the beginning of the universe. This particle horizon currently extends about 46.5 billion light-years in every direction, much larger than 13.8 billion light-years, because the universe has been expanding while the light travels. Any object currently beyond this distance is, by definition, unobservable to us at this moment, regardless of how powerful our telescopes might be. This horizon is not static, but expands at the speed of light as the universe ages. With each passing second, light from slightly more distant regions reaches us for the first time, gradually expanding the volume of space we can observe. In principle, if we could wait long enough, we would eventually see more of the universe. But there's another, more restrictive horizon that limits what we will ever be able to observe, even given infinite time: the cosmic event horizon. Due to the accelerating expansion of the universe, there are regions of space receding from us faster than the speed of light when we account for the expansion of space itself. Light emitted from objects in these regions now will never reach us, no matter how long we wait. This cosmic event horizon currently lies at a distance of approximately 16 billion light-years. Any object presently beyond that distance is forever beyond our observational reach. We can see some of these distant objects as they were in the past, when the universe was smaller and their light could still reach us. But we will never see what they look like today or in the future. Moreover, this event horizon is shrinking over time as the universe's expansion accelerates. Eventually, in the far future, all galaxies beyond our local gravitationally bound group will disappear from view. their light unable to overcome the ever-widening gulf of expanding space. These horizons, particle and event, represent absolute limits to observation, boundaries beyond which we cannot see, regardless of our technology. They remind us that the observable universe is just a subset of the entire universe, and that vast regions of space lie fundamentally beyond our observational reach. But even within the observable universe, there are other limits to what we can detect. The cosmic microwave background radiation, the afterglow of the Big Bang, represents the oldest light we can directly observe with electromagnetic waves. Before this radiation was emitted, approximately 380,000 years after the Big Bang, the universe was opaque to light, filled with a hot, dense plasma of electrons and protons that scattered photons before they could travel far. This cosmic microwave background represents a wall, a boundary to electromagnetic observation. We cannot directly see beyond it with conventional telescopes. It's as if the observable universe is a sphere with the cosmic microwave background forming the inner surface, and us at the center, looking outward in all directions at this ancient light. There are, however, other messengers that could potentially allow us to peer beyond this wall. Neutrinos, nearly massless particles that interact very weakly with matter, decoupled from other particles when the universe was just 1 second old. In principle, if we could detect the cosmic neutrino background, we could see the universe at an even earlier stage. Similarly, gravitational waves, ripples in space-time produced by violent cosmic events, might someday allow us to probe the first fractions of a second after the Big Bang. Unlike electromagnetic waves, gravitational waves can travel unimpeded through the early universe's plasma, potentially carrying information from the earliest moments of cosmic history. But detecting these messengers poses enormous technical challenges. The cosmic neutrino background is predicted to exist, but has not yet been directly observed due to the incredibly weak interactions of low-energy neutrinos with matter. Gravitational waves from the early universe would be extremely faint by the time they reach Earth, requiring detectors far more sensitive than our current technology allows. Even if we could overcome these technical challenges, there would still be fundamental limits to how far back in time we could observe. According to current theories, the very earliest moments after the Big Bang, particularly the Planck epoch, lasting from the beginning until 10 to the negative 43 seconds, involved energies so extreme that our current physics breaks down. We lack a complete theory of quantum gravity, the framework needed to describe the universe under these conditions. This represents another kind of limit to observation, not just practical or technological, but theoretical. We cannot reliably predict what we should be looking for in these earliest moments because our current theories are incomplete. It's a reminder that observation and theory are intertwined. We need theoretical frameworks to interpret our observations, and observations to test and refine our theories. Beyond these physical limits to observation lie philosophical questions about the nature of knowledge itself. What does it mean to know something exists if we can never observe it directly? Can we make meaningful scientific claims about regions beyond our cosmic horizon? These questions touch on long-standing debates in the philosophy of science about realism, instrumentalism, and the status of unobservable entities. Realists argue that successful scientific theories tell us about what actually exists, even if we cannot observe it directly. Instrumentalists counter that theories are merely useful tools for making predictions about observable phenomena, and we should be agnostic about unobservable entities. The multiverse concept, particularly in its more extravagant forms, pushes these philosophical questions to their limits. If other universes exist but are fundamentally unobservable, can their existence be considered a scientific hypothesis rather than a metaphysical speculation? Proponents argue that the multiverse emerges naturally from well-established theories, and that indirect evidence might be available even if direct observation is impossible. Critics counter that without observational tests, multiverse theories risk becoming unfalsifiable, placing them outside the bounds of conventional science. This tension exists not because scientists are unnecessarily speculative or philosophically naive, but because our best theories of physics and cosmology naturally lead us to consider regions and phenomena beyond our direct observational reach. The mathematics that successfully describes what we can observe often points to what we cannot, creating a challenging landscape where observation, theory, and philosophy intersect. Another limit to observation worth considering is quantum uncertainty. According to quantum mechanics, there are fundamental limits to what we can know about physical systems, regardless of how precise our measurements might be. The Heisenberg uncertainty principle tells us that certain pairs of properties, such as position and momentum, cannot both be measured with arbitrary precision simultaneously. This quantum uncertainty extends to vacuum itself. What appears to be empty space is actually a seething quantum foam at the smallest scales, with virtual particles continuously popping in and out of existence, borrowing energy from the vacuum for brief moments allowed by the uncertainty principle. These quantum fluctuations are not just theoretical constructs, but have measurable effects, such as the Casimir force between closely spaced metal plates. Quantum fluctuations in the early universe are thought to be the seeds from which all cosmic structure grew. Tiny quantum jitters in the inflaton field, the field that drove cosmic inflation, were stretched to macroscopic scales by the tremendous expansion of space, eventually becoming the galaxies and galaxy clusters we observe today. This connection between quantum uncertainty and cosmic structure reminds us that the largest scales of the universe are intimately linked to the smallest, that quantum mechanics is not just relevant to atoms and molecules, but to the cosmos as a whole. It suggests that any complete understanding of what lies beyond the observable universe must incorporate quantum principles, even as those principles limit what we can precisely know. There's another kind of observational limit worth considering: the challenge of understanding extreme environments. Black holes represent a prime example. According to general relativity, at the center of a black hole lies a singularity, a point of infinite density where space-time is infinitely curved. Our current physics breaks down at such singularities, unable to describe what actually happens there. Moreover, black holes are surrounded by event horizons, boundaries beyond which nothing, not even light, can escape. Information that falls into a black hole appears to be lost to the outside universe, creating the infamous black hole information paradox that has puzzled physicists for decades. Recent theoretical work suggests that information might not actually be lost, but rather encoded in subtle quantum correlations in the Hawking radiation emitted by black holes as they slowly evaporate. But observational confirmation of these ideas remains extremely challenging, highlighting another limit to our ability to test theories about extreme cosmic environments. Similar challenges arise when studying the conditions of the early universe, the interiors of neutron stars, or the nature of dark energy and dark matter. Each represents an environment or phenomenon that stretches our observational capabilities to their limits, requiring us to rely more heavily on theoretical models and indirect evidence. As we approach these limits of observation, the boundary between physics and philosophy becomes increasingly blurred. Questions that might seem purely scientific, what caused the Big Bang, what preceded it, begin to touch on philosophical issues about the nature of time, existence, causality, and knowledge itself. This blurring doesn't mean we should abandon scientific approaches to these questions. Rather, it suggests that complete answers might require both rigorous science and careful philosophical analysis, working together to clarify what we can know, what we can reasonably infer, and what might lie beyond our reach. The limits of observation also have implications for how we think about the fundamental nature of reality. If significant portions of the universe or multiverse are permanently unobservable to us, should that affect our ontology, our understanding of what ultimately exists? Some philosophers and physicists have proposed variations of what's called the anti-Copernican principle, or the mediocrity principle, suggesting that our observable universe is likely typical rather than special. If we assume we're not in a privileged location or time, then what we observe locally should be representative of the universe more broadly, including parts we cannot see. This principle, if valid, would allow us to make reasonable inferences about unobservable regions based on what we can observe, but it represents a methodological assumption rather than an observational fact, a way of extending our limited perspective rather than directly overcoming it. Others have proposed that we should adopt an informational or relational approach to reality, considering only what can in principle be observed or measured as real in a scientific sense. This perspective, influenced by quantum mechanics and information theory, suggests that reality is fundamentally about relationships and interactions rather than independently existing objects. From this viewpoint, asking about the true nature of unobservable realms might be asking the wrong kind of question. What matters is how different parts of the observable universe relate to each other, how information flows between systems, how consistent patterns emerge from these relationships. These different philosophical approaches highlight the challenge of making sense of the limits of observation. They remind us that when we ask what lies beyond the universe, we're not just asking about distant regions of space, but about the boundaries of knowledge itself, about what can be known and how we can know it. Despite these limits, it's remarkable how much we have been able to learn about the cosmos. Using just the light and other radiation that happens to reach our small planet, we've discerned the age, size, composition, and evolutionary history of the universe. We've detected black holes, neutron stars, exoplanets, gravitational waves, and the afterglow of the Big Bang. We've traced cosmic evolution from the first atoms to the complex galactic structures we see today. This success should give us some confidence that continued observation, combined with theoretical development, will further expand our cosmic understanding. While absolute limits to observation exist, we are far from reaching them with current technology. There remains much to discover within the observable universe that might indirectly inform our understanding of what lies beyond. New telescopes, like the James Webb Space Telescope, new gravitational wave observatories like LISA, new neutrino detectors, and new particle physics experiments continue to extend our observational reach, revealing previously invisible aspects of the cosmos. Each new window on the universe brings the potential for surprises, for observations that challenge our theories and expand our understanding. Theoretical physics also continues to advance, developing more comprehensive frameworks that might bridge quantum mechanics and general relativity, potentially allowing us to better understand the earliest moments of the universe and the nature of black hole singularities. While a complete theory of everything remains elusive, each theoretical advance provides new ways to interpret our observations and suggest new phenomena to look for. The limits of observation are not just barriers, but invitations to develop more creative approaches to cosmic understanding. When direct observation is impossible, we look for indirect evidence, for subtle signatures, for mathematical consistency, for elegant, unifying principles. We develop new instruments, new methodologies, new theoretical frameworks. In this ongoing process, we continuously refine the boundary between the known and the unknown, between what we can observe and what we can only infer, between established science and frontier speculation. This boundary is not fixed, but evolves with our knowledge and capabilities. Some edges are not physical, but are limits of knowing. The boundary of the observable universe is one such edge defined not by a physical wall in space, but by the finite speed of light and the finite age of the universe. The cosmic microwave background represents another, a limit to how far back in time we can directly see with electromagnetic waves. Quantum uncertainty sets yet another, constraining what we can simultaneously know about complementary properties of physical systems. These limits remind us that our cosmic knowledge is always partial, always filtered through the messengers that reach us, always constrained by the fundamental physics that governs observation itself. They humble us, reminding us of how much lies beyond our current understanding, beyond our observational reach, beyond even our theoretical frameworks. Yet they also inspire us to push against these boundaries, to develop new ways of seeing, new frameworks for understanding, new approaches to the greatest cosmic questions. In acknowledging the limits of observation, we honor both what we know and what we have yet to discover, both the vastness of the cosmic story we've uncovered and the even greater vastness that remains to be explored. Whether or not we can ever directly observe what lies beyond our universe, the very act of questioning, of theorizing, of imagining possibilities beyond our observational horizon represents a uniquely human endeavor, one that connects us to the cosmos even as it reminds us of our limitations. In the space between knowing and unknowing, between observation and theory, between science and philosophy, we find not just the limits of our understanding, but the endless frontier of discovery. A loop has no edge. But still, what holds the loop? As we contemplate what might lie beyond the universe, we've explored several possibilities. Perhaps space extends infinitely in all directions. Perhaps our universe is one bubble in a vast multiverse. Perhaps fundamental limits to observation prevent us from ever knowing for certain. But there's another intriguing possibility worth considering. Could the universe be finite in size, yet have no boundary or edge? This concept can be difficult to grasp because it contradicts our everyday experience. In our normal three-dimensional world, finite objects always have boundaries. A ball has a surface that marks its edge. A book has covers that define its limits. A room has walls that bound the space within. How could something be finite yet have no boundary? The key to understanding this possibility lies in the concept of curvature and topology. The most familiar example is the surface of a sphere like our planet Earth. The Earth's surface is finite. It has a definite area that can be measured, yet it has no edge or boundary. You could walk in any direction on the Earth's surface forever, never reaching an edge, eventually returning to your starting point. This property of being finite yet boundless emerges from the positive curvature of the sphere's surface and its closed topology. It's a two-dimensional surface curved through a third dimension in a way that allows it to close back on itself without creating any edges. Could our three-dimensional space have a similar property? Could it curve through a fourth spatial dimension in a way that makes it finite yet boundless, allowing someone traveling in a straight line to eventually return to their starting point? This possibility was first seriously explored by Albert Einstein when he developed general relativity, his revolutionary theory of gravity. According to general relativity, space itself can curve in response to mass and energy. The distribution of matter and energy throughout the cosmos determines the overall geometry of space, whether it's flat, positively curved like a sphere, or negatively curved like a saddle. If space has an overall positive curvature and a closed topology, then the universe would indeed be finite yet boundless. It would contain a finite volume of space and a finite amount of matter, yet it would have no edge or boundary. It would be complete unto itself, with no need for anything beyond it, at least not in the conventional spatial sense. The classic analogy used to explain this concept is to imagine beings living on the surface of a balloon. To these two-dimensional creatures, their universe is the surface of the balloon, which is finite in area. But they could travel forever in what seems to them a straight line, eventually returning to their starting point. There is no edge to their universe, no boundary where it stops. From the perspective of these balloon beings, there is no beyond their universe in the ordinary sense of the word. Their universe is complete, self-contained, a closed system. But we, existing in 3 dimensions, can see that their 2-dimensional universe is embedded in our higher dimensional space. We can see inside and outside the balloon, concepts that would be meaningless to the balloon beings. Similarly, our 3-dimensional space might be curved through a 4th spatial dimension, in a way that makes it finite, yet boundless. We cannot visualize this 4th dimension, just as the balloon beings cannot visualize our 3rd dimension. But mathematically, it's a perfectly coherent possibility. If the universe does have this geometry, then light itself would curve along with space, following what are called geodesics, the shortest paths through curved space-time. If you could shine a powerful enough laser beam in one direction and wait long enough, you might eventually see the beam return from the opposite direction, having traveled all the way around the universe. Similarly, if you looked far enough in one direction with a powerful enough telescope, you might see the back of your own head, or rather, your galaxy, as it was billions of years ago. The light from the Milky Way would have had time to travel all the way around the universe and back to us. This possibility raises an intriguing observational test. If the universe is finite and small enough, we might observe repeated patterns in the cosmic microwave background radiation, or in the distribution of distant galaxies. We would be seeing the same regions of space from different angles and at different times in their history. Astronomers have searched for such matched circles in the cosmic microwave background, patterns that would indicate light has traveled multiple paths around a finite universe to reach us. So far, no convincing evidence for such patterns has been found, suggesting that if the universe is finite, it's larger than the observable universe. Current observations of the cosmic microwave background indicate that the universe is remarkably close to flat, with any curvature being so slight as to be nearly undetectable with current methods. This flatness poses a puzzle for the finite but unbounded model, as a perfectly flat universe would extend infinitely rather than curving back on itself. However, there's an important distinction between geometry and topology. Geometry describes the local curvature of space, while topology describes how space connects globally. Even a flat space can have an interesting topology that causes it to connect back to itself, creating a finite volume. Imagine a flat sheet of paper. Its geometry is Euclidean, following the rules of flat space. But if you connect the opposite edges to each other, the left edge to the right edge and the top edge to the bottom edge, you create what mathematicians call a torus, or donut shape. The geometry remains flat at every point, yet the space is now finite and has an interesting connectivity. Such a space is called multi-connected because there are multiple paths between any 2 points. If you shoot a laser beam in one direction, it would eventually return to its starting point, possibly from a different direction, depending on the specific topology. Our three-dimensional space could theoretically have analogous properties, connecting back on itself in various ways while maintaining its flat or nearly flat geometry. If this were the case, the universe could be finite despite its flat geometry. Cosmologists have considered several possible topologies for a finite universe: the three-dimensional torus or hypertorus, the Poincare dodecahedral space, the weak space, and others. Each represents a different way that flat or nearly flat space might connect back on itself in higher dimensions. If the universe does have such a topology, it would mean that the cosmos is like a hall of mirrors, with the same regions of space appearing multiple times from different directions when viewed from sufficiently large distances. Light would traverse the entire volume of space and return to its starting point, perhaps multiple times. This finite but unbounded model has several philosophical implications. It provides a way to have a universe that is both finite and complete, with no edge or boundary, no outside in the conventional spatial sense. It avoids the puzzling question of what lies beyond the edge of the universe by eliminating the edge entirely. It also addresses some of the conceptual difficulties associated with an infinite universe. Infinity is a challenging concept both mathematically and philosophically. An infinite universe raises questions about countability, about whether infinity is a physical reality or merely a mathematical abstraction. A finite but unbounded universe sidesteps these difficulties while still avoiding the problem of a boundary. But the finite but unbounded model also raises its own philosophical questions. If our three-dimensional space curves through a fourth spatial dimension, what is the nature of this dimension? Is it physical or merely a mathematical construct that helps us visualize the curvature of space? In some theories, particularly certain versions of string theory, extra spatial dimensions are posited to exist physically, not just mathematically. These dimensions might be compactified, curled up so tightly they're undetectable at ordinary energies, or they might be extended, with our three-dimensional universe existing as a membrane or brain within this higher dimensional space. If these extra dimensions exist physically, then what lies beyond our universe might indeed be a higher dimensional bulk space, potentially containing other brains, other three-dimensional universes floating in the same higher dimensional medium. This brings us back to the multiverse concept from a different angle. Our universe might be finite yet boundless in 3 dimensions, while still being embedded in a higher dimensional space along with other universes. What lies beyond the universe would then be a matter of dimensional perspective rather than spatial extent. But all of this remains speculative. Current observations support a flat or nearly flat geometry for the observable universe, but they cannot definitively determine whether the universe is infinite or finite with an interesting topology. The overall structure of space remains one of the great unanswered questions in cosmology. The finite but unbounded model also intersects with questions about the origin and evolution of the universe. The Big Bang Theory describes the evolution of the universe from an extremely hot, dense state, but it doesn't necessarily imply that the universe began as a dimensionless point. If the universe is finite but unbounded, like a 3-dimensional analog of a sphere's surface, then the Big Bang might be better understood not as a beginning from a point, but as a minimum size state, with the entire closed universe compressed to its smallest possible volume. As the universe expanded, this volume increased, but the topology remained the same, finite yet boundless. This perspective shifts our understanding of cosmic evolution. Rather than an explosion outward from a central point into pre-existing space, the Big Bang would represent the simultaneous expansion of all points in a closed, self-contained cosmos. The future evolution of such a universe depends on the balance between the expansion rate and the gravitational pull of matter. If there's enough matter, or if dark energy weakens over time, the expansion might eventually halt and reverse, leading to a big crunch where the universe contracts back to a hot, dense state. This oscillating model, with repeated cycles of expansion and contraction, was once popular but has fallen out of favor with the discovery of accelerating cosmic expansion driven by dark energy. Current observations suggest that the universe will continue to expand forever, regardless of whether it's finite or infinite. But a finite, closed universe with a specific topology places constraints on this expansion. The volume can increase indefinitely, but the connectivity remains fixed. It's like inflating a balloon. The surface area increases, but the fact that it forms a closed surface doesn't change. This raises an interesting question about the ultimate fate of a finite but unbounded universe. If expansion continues forever, driven by dark energy, the universe would become increasingly sparse, with galaxies moving farther apart and eventually disappearing beyond each other's cosmic event horizons. But the topology would remain, a ghostly structure connecting emptier and emptier regions of space. The finite but unbounded model also affects how we think about the total content of the universe. An infinite universe would contain an infinite amount of matter and energy, raising difficult questions about totality and comprehensibility. A finite universe would contain finite amounts, making the cosmic inventory more conceptually manageable, even if still vast beyond ordinary comprehension. But while a finite universe might be more philosophically satisfying in some ways, we must be careful not to let aesthetic or philosophical preferences influence our scientific assessment. The question of whether the universe is finite or infinite, bounded or boundless, must ultimately be decided by observation and measurement, not by which model we find more elegant or intuitive. Current observations, particularly of the cosmic microwave background radiation, place constraints on the size and topology of the universe. If the universe is finite with a non-trivial topology, then the scale of this topology must be larger than the observable universe, or we would have detected signs of it in the pattern of temperature fluctuations in the cosmic microwave background. Future observations with more sensitive instruments might reveal subtle signatures of a finite but unbounded universe. For example, gravitational waves, ripples in space-time produced by violent cosmic events, might show patterns indicating they have traveled multiple paths around a finite universe. Or future maps of the cosmic microwave background might reveal the subtle matching patterns expected in a multi-connected space. Until such evidence is found, the question remains open. The universe might be infinite and flat, extending endlessly in all directions, or it might be finite yet boundless, curving back on itself in higher dimensions without any edge or boundary, or it might have some more exotic structure that we have yet to fully understand or imagine. The concept of a finite but unbounded universe reminds us of the profound ways in which reality might differ from our everyday intuitions. Our experience of the world is limited to a tiny region of space, a brief moment in cosmic history, a narrow range of scales between the subatomic and the planetary. When we contemplate the universe as a whole, we must be prepared to transcend these limitations to embrace possibilities that challenge our preconceptions. A loop has no edge, but still, what holds the loop? This question itself may be based on a misconception, an assumption that a self-contained, finite yet boundless universe needs something outside itself to hold it or give it context. In a truly self-contained cosmos, there would be no need for an external support or container. This doesn't mean we couldn't posit a higher dimensional space in which our three-dimensional universe is embedded. Such a space might exist, and other universes might float alongside our own in this higher dimensional bulk. But this higher space wouldn't be necessary to explain the existence or stability of our universe. It would simply be another level of reality, another layer of the cosmic onion. The finite but unbounded model offers a middle path between the two extremes of an infinite, boundless cosmos extending forever in all directions, and a finite universe with an edge or boundary beyond which nothing exists. It suggests a universe that is complete unto itself, self-contained, with a definite size and content yet no limit or border. Takes on a different meaning. There is no beyond in the conventional spatial sense, no exterior to explore, no edge to cross. And yet, we might still conceive of a beyond in other dimensions, other levels of reality, other frameworks of existence outside our familiar three-dimensional space. As we contemplate these possibilities, we are reminded of the limitations of our spatial intuitions, our three-dimensional thinking, our everyday experience of boundaries and edges. The universe may be structured in ways that transcend these familiar categories, ways that require new concepts, new mathematics, new modes of thought to fully comprehend. A finite but unbounded universe invites us to expand our conceptual horizons, to imagine space curved through higher dimensions, to envision a cosmos that is both limited and limitless, both contained and boundless. It challenges us to think beyond the dichotomy of finite versus infinite, bounded versus boundless, to explore the rich possibilities that lie in between. Whether the universe is indeed finite but unbounded remains an open question, one that current observations cannot definitively resolve. But in considering this possibility, in stretching our minds to encompass it, we participate in the great cosmic adventure of discovery, the quest to understand the true nature of the universe we inhabit. A loop has no edge, but still, what holds the loop? Perhaps nothing holds it. Perhaps it holds itself complete and self-contained, a cosmic circle with no beginning or end, no inside or outside, no before or after. Or perhaps it drifts in a higher dimensional sea, along with countless other loops, other universes, other realms of existence. The answer lies at the frontier of cosmology, at the boundary between what we know and what we have yet to discover about the ultimate nature of reality. If we live on one layer, what lies beneath or beyond? So far in our exploration of what might lie beyond the universe, we've primarily considered extensions of our familiar three-dimensional space, infinite universes, bubble universes in a multiverse, finite but unbounded geometries. But there's another intriguing possibility. What if beyond isn't about distance at all, but about dimensionality? What if there are additional dimensions beyond the three spatial dimensions we experience, dimensions that might harbor other realms of existence? This idea isn't just science fiction. Several major frameworks in theoretical physics suggest that extra dimensions might really exist, hidden from our everyday experience, but fundamental to the deep structure of reality. Let's explore these hidden dimensions and what they might mean for our understanding of what lies beyond the universe. Our everyday experience is firmly rooted in three spatial dimensions: up-down, left-right, and forward-backward. Combined with time, these dimensions form the four-dimensional space-time that Einstein's relativity describes so successfully. For most of scientific history, these four dimensions seem sufficient to explain the physical world. But in the latter part of the 20th century, theoretical physicists began to explore the possibility that additional spatial dimensions might exist. This exploration wasn't driven by wild speculation, but by attempts to solve fundamental problems in physics, particularly the challenge of unifying gravity with the other fundamental forces. The most prominent framework suggesting extra dimensions is string theory, which proposes that the fundamental building blocks of reality are not point-like particles, but tiny, vibrating strings. These strings are so small, about 10 to the negative 35th meters, that they would appear as particles to our most powerful instruments. In string theory, the different vibration patterns of these strings create the different particles we observe: electrons, quarks, photons, and so on. It's similar to how different vibration patterns on a violin string produce different musical notes. But for the mathematics of string theory to work consistently, something surprising is required. The universe must have more than three spatial dimensions. Depending on the specific formulation, string theory typically calls for 6 or 7 additional spatial dimensions, for a total of 9 or 10 spatial dimensions plus time. If extra dimensions exist, why don't we notice them? Why does our experience seem firmly three-dimensional? String theory suggests two possibilities. Either these extra dimensions are compactified, curled up so tightly that they're undetectable at ordinary energies, or our three-dimensional universe exists as a membrane or brain within a higher dimensional space, with the extra dimensions extending perpendicular to our brain. Let's consider the compactification scenario first. Imagine an ant walking along a garden hose viewed from a distance. To the distant observer, the ant appears to move in just one dimension along the length of the hose. But the ant actually has another option. It can move around the circumference of the hose as well. This circular dimension is too small for us to easily notice from afar, but it's very real to the ant. Similarly, the extra dimensions proposed by string theory might be curled up into incredibly tiny circles or more complex shapes called Calabi-Yau manifolds, with sizes on the order of the Planck length, far smaller than anything we can directly probe with current technology. These dimensions would exist at every point in our familiar three-dimensional space, like tiny, intricate origami structures folded into the fabric of reality. If these compactified dimensions exist, what would they mean for our question about what lies beyond the universe? In one sense, they wouldn't provide a beyond in terms of vast new realms of space. Rather, they would represent a beyond in terms of complexity, a hidden structure underlying what we perceive as fundamental particles and forces. The specific ways these extra dimensions are compactified would determine the properties of particles and forces in our observable universe. Different compactification patterns could, in principle, create different sets of physical laws. This connects to the multiverse idea we explored earlier. Different regions of the multiverse might have different compactification patterns, leading to different physics. But there's another possibility for extra dimensions that offers a more dramatic vision of what might lie beyond: the brainworld scenario. Our universe doesn't include the additional dimensions. It sits within them, like a sheet of paper in three-dimensional space. In this picture, all the fundamental particles and forces we know, electrons, quarks, photons, the strong and weak nuclear forces and electromagnetism, are confined to our brain. They can't leave our three-dimensional universe because they're fundamentally three-dimensional objects. It's as if they're like water droplets that can move freely on the surface of a pond but can't leave the surface to fly into the air. Gravity, however, is different. As Einstein showed, gravity isn't a force in the conventional sense but a curvature of space-time itself. This unique nature might allow gravity to leak into the extra dimensions, explaining why gravity appears so much weaker than the other fundamental forces. Its influence is spread through more dimensions, diluting its strength in our three-dimensional world. If our universe is indeed a brain in a higher dimensional bulk, what else might exist in this higher dimensional space? One intriguing possibility is that other brains, other three-dimensional universes, might exist alongside our own, perhaps separated by only a tiny distance in the extra dimensions. These parallel brains would be completely invisible to us through conventional observation. Light and all other forms of electromagnetic radiation would be confined to each brain, unable to cross the higher dimensional gap between them. It would be like two parallel sheets of paper, each with its own two-dimensional world drawn on it, unable to see what's on the other sheet. But gravity might still provide a connection. If gravity can indeed leak through the extra dimensions, then matter on one brain could gravitationally influence matter on another. This gravitational interaction across brains could potentially explain dark matter or dark energy, those mysterious components that make up 95% of the universe's energy content. Some versions of brainworld theory even suggest that the Big Bang, the explosive beginning of our universe, might have been caused by a collision between our brain and another. The enormous energy of this collision could have created all the matter and radiation in our universe, initiating the cosmic expansion we observe today. This scenario offers a dramatic vision of what might lie beyond our universe. Other universes, other brains floating in the same higher dimensional bulk space, occasionally interacting through gravity or high-energy collisions. These other universes might have different physical laws, different types of matter and energy, different histories of cosmic evolution. Both the compactified and brainworld scenarios for extra dimensions remain speculative. While they emerge from mathematically consistent theories, we have yet to find direct experimental evidence for the existence of extra dimensions. Scientists have searched for signs of extra dimensions in particle accelerator experiments, gravitational wave observations, and precise measurements of gravity at small scales. But so far, no conclusive evidence has been found. This doesn't mean extra dimensions don't exist. They might simply be too small or too weakly interacting to detect with current technology. Or the specific properties of these dimensions might differ from our simplest models, requiring more sophisticated search strategies. Beyond string theory, there are other theoretical frameworks that suggest the existence of hidden realms. Quantum field theory, the mathematical framework underlying the standard model of particle physics, describes a complex structure of fields permeating all of space. These fields represent the different fundamental forces and particles, existing in a kind of abstract space of possibilities. In quantum field theory, the vacuum, what we might think of as empty space, is not truly empty, but filled with quantum fields in their lowest energy states. These fields undergo constant fluctuations due to the uncertainty principle, with virtual particles briefly popping into existence and then disappearing. This quantum vacuum is a kind of hidden realm underlying all of physical reality, a seething sea of potential beneath the apparent calm of empty space. Some speculative theories suggest that the quantum vacuum might be even more complex than current models indicate, potentially harboring parallel realities or additional dimensions. For instance, in the many worlds interpretation of quantum mechanics, reality branches into multiple paths with each quantum event, creating a vast tree of alternate histories. These alternate realities wouldn't exist in our space, but in an abstract space of quantum possibilities. Another concept worth exploring is the holographic principle, which suggests that all the information contained in a volume of space can be represented on a boundary enclosing that space. This principle emerges from studies of black hole thermodynamics and has been developed into formal frameworks like the ADS-CFT correspondence in string theory. In the holographic picture, our three-dimensional reality might be encoded on a two-dimensional surface, similar to how a hologram on a credit card creates the illusion of a three-dimensional image. This doesn't mean our experience of three dimensions is an illusion, but rather that the fundamental description of reality might require one fewer dimension than we perceive. If the holographic principle is correct, what lies beyond our universe might not be additional space or even additional dimensions, but a more fundamental level of reality, a simpler description from which our complex three-dimensional experience emerges. The beyond would be not spatial, but ontological, a deeper level of existence. These various frameworks, string theory, brain worlds, quantum field theory, the many worlds interpretation, the holographic principle, offer different visions of what might lie beyond our familiar three-dimensional universe. Some suggest physical realms in higher dimensions, others more abstract spaces of quantum possibilities, others more fundamental levels of descriptive reality. What unites these diverse ideas is a common suggestion: reality is richer, more complex, more multi-layered than our ordinary experience indicates. The three spatial dimensions we navigate daily might be just one aspect of a much more intricate cosmic structure, one facet of a multifaceted reality. In everyday language, beyond implies a spatial relationship. Something is beyond a boundary if it lies on the other side of that boundary. The concept of other dimensions also intersects with various cultural and spiritual traditions that have long spoken of other realms existing alongside our own. From the multiple heavens and hells of various religious traditions to the subtle realms of certain Eastern philosophies, humans have often intuited the possibility of worlds beyond ordinary perception. While modern physics arrives at the concept of other dimensions through mathematical reasoning rather than spiritual insight, there's a fascinating confluence in the basic intuition that reality might be more than what we directly perceive. The scientific models provide specific, mathematically rigorous frameworks for understanding how such extra dimensions might work, offering the potential for empirical testing that earlier intuitions lacked. One practical consequence of these ideas about extra dimensions is that they suggest new avenues for experimental physics. If extra dimensions exist, they might leave detectable signatures in high-energy particle collisions, precise measurements of gravitational forces at small distances, or the properties of gravitational waves from distant cosmic events. Scientists at facilities like the Large Hadron Collider have searched for evidence of extra dimensions by looking for unusual patterns in particle collisions, or the apparent creation of particles that immediately disappear into other dimensions. So far, these searches have not found definitive evidence, but they have set constraints on the possible sizes and properties of extra dimensions. Another approach is to look for deviations from the expected behavior of gravity at very small distances. According to some brain-world models, gravity's strength should increase more rapidly than expected at scales smaller than the size of the extra dimensions, as its influence becomes confined to fewer dimensions. Precision experiments testing gravity at microscopic scales have not yet seen such deviations, but continue to push the boundaries of measurement. Gravitational wave astronomy provides another potential window into extra dimensions. If gravity propagates through higher dimensions, gravitational waves might show subtle effects not predicted by conventional general relativity. As gravitational wave observatories become more sensitive, they might detect such effects if extra dimensions exist. These ongoing experimental efforts remind us that the concept of other dimensions is not merely philosophical speculation, but a scientific hypothesis with potential empirical consequences. While the existence of extra dimensions remains unconfirmed, it represents a testable prediction of certain theoretical frameworks, placing it firmly within the realm of scientific inquiry. If extra dimensions do exist, what would they mean for our understanding of reality and our place within it? Would they fundamentally change our conception of what lies beyond the universe? In one sense, extra dimensions would expand our notion of beyond from a purely spatial concept to a dimensional one. The cosmic horizon would become not just a boundary in three-dimensional space, but a dimensional barrier, with reality continuing in directions we cannot directly perceive or navigate. This dimensional perspective might also change how we think about fundamental questions in cosmology. The beginning of the universe might not have been a beginning of all reality, but a transition or event within a higher dimensional framework. The apparent fine-tuning of physical constants might result from selection processes operating across a landscape of possibilities in extra dimensions. The dark matter and dark energy that dominate our universe's energy budget might represent interactions with other dimensional realms. Perhaps most profoundly, the existence of extra dimensions would remind us once again of the limits of our perception and the vastness of what might exist beyond our direct experience. Just as the discovery of galaxies beyond the Milky Way expanded our cosmic perspective, the confirmation of extra dimensions would represent another step in humanity's ongoing journey from a narrow, Earth-centered worldview to a broader, multi-dimensional understanding of reality. This doesn't mean we should uncritically accept every speculative theory about extra dimensions or parallel realities. Scientific progress depends on maintaining a careful balance between imaginative exploration and rigorous testing, between theoretical possibilities and empirical constraints. The concept of extra dimensions must ultimately stand or fall based on observational evidence, not just mathematical elegance or philosophical appeal. Nevertheless, the very fact that serious scientific theories suggest the possibility of hidden dimensions invites us to expand our thinking, to consider realities beyond our immediate perception, to imagine cosmic structures more complex and multi-layered than our everyday experience indicates. If we live on one layer, what lies beneath or beyond? Perhaps other layers, other brains, other universes floating in the same higher dimensional space. Perhaps compact dimensions curled up at every point, their intricate structures determining the fundamental properties of particles and forces. Perhaps quantum branches, alternate histories unfolding in parallel alongside our own. Perhaps a more fundamental level of reality from which our three-dimensional experience holographically emerges. Or perhaps combinations of these possibilities, or something even more surprising that we have yet to conceive. The history of cosmology suggests humility about the limits of our current understanding. Each major advance has revealed the cosmos to be stranger, more wonderful, more surprising than we had previously imagined. The concept of other dimensions reminds us that what lies beyond the universe might not be more universe, at least not in the familiar three-dimensional sense. It might be other dimensions, other frameworks of existence, other levels of reality structured in ways we struggle to visualize, but can describe mathematically. In contemplating these possibilities, we participate in one of humanity's most noble endeavors, the quest to understand the true nature of reality, to see beyond the limitations of our immediate perception, to glimpse the deeper structures underlying the cosmos we inhabit. Whether or not extra dimensions ultimately prove to exist, the exploration of their possibility expands our cosmic perspective, challenging us to think beyond our three-dimensional intuitions, to consider the full richness of what might lie beyond. Where the fabric tears, could a new space begin? Throughout our journey, exploring what might lie beyond the universe, we've considered possibilities ranging from infinite cosmic expansion to multiple dimensions. But there's another intriguing possibility to contemplate. Could there be natural bridges or tunnels connecting different regions of our universe, or perhaps even linking our universe to others? The most promising candidates for such cosmic connections are among the most extreme objects in the cosmos: black holes. Black holes represent the ultimate cosmic mystery, regions where matter has collapsed to such incredible density that space and time themselves are dramatically warped. At the heart of every black hole lies what physicists call a singularity, a point where, according to our current theories, density becomes infinite, and the laws of physics, as we understand them, break down completely. These extraordinary objects are defined by their event horizons, boundaries in space beyond which nothing, not even light, can escape. Once something crosses this horizon, its fate is sealed, inexorably drawn toward the singularity, unable to return or communicate with the outside universe. For decades, black holes were viewed primarily as cosmic dead ends, places where matter and information are lost forever. But theoretical developments over the past half-century have suggested a more complex and intriguing possibility. Black holes might be more than just one-way tickets to oblivion. They might connect to other places, other times, perhaps even other universes. The mathematical framework that first seriously explored this possibility was developed by Albert Einstein and Nathan Rosen in 1935. They discovered that the equations of general relativity allowed for solutions called Einstein-Rosen bridges, structures that connect two different regions of spacetime. These theoretical constructs later became popularly known as wormholes. In their simplest form, wormholes could connect two distant regions of our own universe, potentially providing shortcuts across vast cosmic distances. Imagine folding a piece of paper so that two distant points touch, then punching a hole connecting them. This provides a rough analogy for how a wormhole might create a passage through higher dimensional space, connecting remote regions of our three-dimensional universe. But more exotic possibilities exist. Some theoretical models suggest wormholes could connect to entirely different universes, or to different times within our own universe, or to regions with different physical constants or even different dimensionality. If such connections exist, black holes might not be cosmic dead ends but cosmic gateways, passages to realms beyond our observable universe. This possibility emerges most clearly in the maximal extension of the Schwarzschild solution, the mathematical description of a non-rotating black hole. When fully worked out, this solution reveals not just a black hole, but a paired structure. A black hole connected to a white hole through a tunnel-like throat. While a black hole allows things to enter but not leave, a white hole would allow things to leave but not enter. Essentially a time-reversed black hole. Matter and energy would spontaneously emerge from a white hole, as if from nowhere, the exact opposite of a black hole's behavior. Together, this black hole-white hole pair, connected by a wormhole throat, could theoretically link two separate regions of spacetime. Matter falling into the black hole would, according to these mathematical solutions, emerge from the white hole, potentially in a different region of our universe, or even in another universe entirely. However, these simple wormhole solutions face a serious problem. They're not traversable. The throat connecting the black and white holes pinches off so quickly that nothing, not even light, could pass through before the connection closes. Any attempt to travel through such a wormhole would be futile. The passage would close before the journey could be completed. Moreover, the interior of a realistic black hole is not static but dynamic. The singularity isn't just a point in space, but a moment in the future, toward which everything within the event horizon inevitably moves. This time-like nature of the singularity further complicates the wormhole picture. making passage even more problematic. Yet, theoretical physicists are nothing if not persistent in exploring possibilities. In 1988, physicist Kip Thorne and his colleagues proposed that a sufficiently advanced civilization might be able to create and maintain a traversable wormhole by threading it with exotic matter, material with negative energy density that could hold the throat open against its tendency to collapse. While exotic matter sounds like science fiction, quantum field theory actually predicts certain situations where negative energy densities can briefly exist, such as in the Casimir effect, where quantum fluctuations between closely spaced plates create a small negative pressure. However, the amount of exotic matter needed to hold open a macroscopic wormhole would be enormous, far beyond anything we can currently produce or manipulate. Even if traversable wormholes could exist, they would likely be extraordinarily unstable. The slightest perturbation, even a single photon passing through, might be enough to destabilize the delicate configuration, causing the wormhole to collapse or transform into a black hole. Despite these challenges, the theoretical possibility of wormholes connecting different regions of space-time remains intriguing. If such connections exist, they could provide a physical basis for what might lie beyond our universe, not in some abstract philosophical sense, but in a concrete, potentially observable way. In recent years, the connection between black holes and possible bridges to other realms has been explored in the context of quantum gravity, the still developing framework that aims to reconcile general relativity with quantum mechanics. One of the most promising approaches is the anti-de Sitter conformal field theory, ADES-CFT correspondence, a theoretical framework suggesting that gravity in a curved space-time might be mathematically equivalent to a quantum field theory operating on the boundary of that space-time. This correspondence implies a kind of holographic relationship, where the physics of a three-dimensional realm is encoded on a two-dimensional surface, similar to how a hologram on a credit card creates the illusion of a three-dimensional image. In this framework, black holes take on a new significance. The entropy of a black hole, a measure of its internal disorder or information content, is proportional not to its volume, but to its surface area. This surprising property aligns with the holographic principle, suggesting that what appears to be information lost within a black hole might actually be preserved in a different form on its event horizon. Some speculative models based on this approach suggest that black holes might be understood as highly entangled quantum systems connecting different regions of space-time. The apparent loss of information when something falls into a black hole might represent a transfer of that information to another region or another level of reality, rather than true destruction. This connects to another intriguing concept: black hole complementarity. According to this principle, the description of what happens to an object falling into a black hole depends on the observer's perspective. To an external observer, the object never quite crosses the event horizon, but instead becomes increasingly red-shifted and time-dilated, eventually appearing to freeze at the horizon's edge. Meanwhile, from the falling object's perspective, it crosses the horizon without noticing anything special at that boundary, continuing inward toward the singularity. These two descriptions appear contradictory, but might be complementary in the quantum sense. Different valid perspectives on the same underlying reality, similar to how light can be correctly described as both a wave and a particle, depending on the experimental context. In recent years, this picture has been further complicated by the firewall paradox, which suggests that quantum effects near the event horizon might create a region of intense energy, a firewall that would incinerate anything falling in. This contradicts the principle of general relativity that nothing special should happen at the event horizon from the perspective of a falling observer. These ongoing theoretical puzzles highlight the extent to which black holes represent a frontier in our understanding, a place where our best theories of physics come into tension and potentially break down. And it's precisely this theoretical tension that makes black holes such promising candidates for cosmic bridges to realms beyond our observable universe. Another fascinating connection between black holes and possible cosmic bridges comes from inflation theory. As we've discussed in earlier chapters, cosmic inflation was an extremely rapid expansion of space in the earliest moments after the Big Bang. This process likely created our observable universe, but it might not have stopped everywhere at once. In the eternal inflation scenario, the inflationary process continues indefinitely in some regions while stopping in others, creating bubble universes within a vast, ever-inflating sea. These bubble universes might have different physical properties, different constants of nature, different effective dimensionality. Some theoretical models suggest that the formation of black holes might be connected to this bubble universe creation process. In these scenarios, the singularity at the heart of a black hole isn't a true ending, but a new beginning, a seed for a baby universe branching off from our own. The extreme warping of space-time near the singularity creates the conditions for a new inflationary process to begin, essentially birthing a new universe. These baby universes would not exist within our space, but would form their own space-time, connected to ours only at the initial singularity. From our perspective, the black hole would still appear to contain a singularity, an endpoint, but the reality might be a new cosmic beginning, a fresh Big Bang creating a universe that expands into its own dimensional framework. If this scenario is correct, every black hole in our universe, and there are billions in our galaxy alone, might be the birthplace of a new universe, with slightly different properties inherited from the specific conditions of its parent black hole. Our own universe might itself be the result of a black hole in a parent universe, part of an endless chain of cosmic reproduction. This concept of black holes as universe generators connects to the intriguing observation that the fundamental constants of our universe appear remarkably well tuned for the production of black holes. Some physicists, most notably Lee Smolin, have proposed a kind of cosmic natural selection, where universes that produce more black holes have more offspring universes, potentially explaining the specific values of fundamental constants we observe. Whether or not black holes truly connect to other universes remains speculative. The mathematics of general relativity suggests these possibilities, but the full integration of quantum effects near singularities, where quantum gravity becomes essential, remains incomplete. We simply don't yet have a comprehensive theory that can definitively describe what happens at the heart of a black hole. Yet another possible connection between black holes and bridges to other realms comes from string theory. In this framework, elementary particles are not point-like, but tiny, vibrating strings, whose different vibration patterns create different particle types. For the mathematics of string theory to work consistently, additional spatial dimensions beyond the familiar three are required, typically compactified or curled up at scales too small to directly detect. In some string theory scenarios, black holes might connect not just to other regions of our universe, but to these hidden dimensions or to brains, three-dimensional membranes floating in higher dimensional space. What appears to us as matter disappearing into a black hole might represent a transfer to these higher dimensions or alternate branes. The extreme conditions near a black hole singularity might temporarily uncompactify these hidden dimensions, creating a passage to realms that are normally inaccessible from our three-dimensional perspective. Or they might thin the barrier between our brain and others, allowing for interaction between otherwise separate cosmic domains. These string-theoretic possibilities remain highly speculative, but represent another way in which black holes might serve as bridges to realms beyond our observable universe. The underlying mathematics, while incomplete, consistently points toward black holes as places where the conventional boundaries of space-time break down, where passages to other regions, times, or even universes might exist. Beyond these theoretical considerations, astronomers have sought observational evidence that might shed light on the nature of black holes and their possible connections to other realms. The Event Horizon Telescope collaboration made headlines in 2019 when it released the first direct image of a black hole's shadow, a dark region surrounded by a bright ring of light bent by the black hole's gravity. This remarkable achievement confirmed the basic prediction of general relativity regarding the appearance of black holes, but it couldn't reveal what happens beyond the event horizon. No direct observation can show us what occurs inside a black hole, as no signal can emerge from beyond this cosmic point of no return. However, indirect observations continue to provide clues. The gravitational waves detected by LIGO and Virgo, ripples in space-time produced by colliding black holes, offer a new window into these extreme objects. The specific pattern of these waves confirms that black holes behave as general relativity predicts, at least in their external properties and interactions. Future gravitational wave observatories, particularly space-based ones like the proposed LISA mission, will provide even more precise measurements of black hole properties. These observations won't directly reveal whether black holes connect to other universes, but they might show subtle deviations from the predictions of general relativity, potentially hinting at new physics relevant to these cosmic connections. Another approach comes from studying what happens when matter falls into a black hole. While we can't see beyond the event horizon, we can observe the intense radiation emitted as material spirals inward, forming an accretion disk heated to millions of degrees. The specific patterns of X-rays and other radiation from these disks provide information about the space-time near the black hole. Some speculative models suggest that if black holes do connect to other universes or regions, there might be subtle signatures in this radiation. For instance, quantum effects near the horizon might create patterns of correlation in the emitted particles that indicate connections to other realms. The possible link between black holes and cosmic bridges also raises fascinating philosophical questions. If black holes do connect to other universes or regions, what happens to the information about objects that fall in? Does it truly transfer to another realm? Or is it somehow preserved in our universe, perhaps encoded on the event horizon, as suggested by the holographic principle? This black hole information paradox has puzzled physicists for decades and touches on fundamental questions about the nature of information, causality, and quantum mechanics. Recent theoretical work suggests that information might not actually be lost, but rather highly scrambled and preserved in subtle quantum correlations in the Hawking radiation emitted by black holes as they slowly evaporate. If this is correct, then black holes represent not true cosmic bridges, but rather extremely complex quantum systems that preserve information in unexpected ways. The apparent connection to other realms would be a kind of illusion, a misinterpretation of the black hole's complex quantum nature. But other approaches maintain the possibility of genuine cosmic bridges. In the fuzzball proposal from string theory, black holes don't actually contain singularities, but rather extremely dense, quantum mechanical objects with entropy proportional to their surface area. These fuzzballs might connect to other parts of the multiverse through quantum entanglement, creating effective bridges without the problematic singularities of classical black hole models. Regardless of which theoretical approach ultimately proves correct, the study of black holes continues to push the boundaries of our understanding, challenging us to consider possibilities beyond our conventional cosmic perspective. They represent places where space and time as we understand them break down, where the familiar rules of physics reach their limits, where passages to realms beyond our observable universe might exist, where the fabric tears. Could a new space begin? The mathematics of our best physical theories suggests this intriguing possibility. At the heart of a black hole, where space-time is stretched to its breaking point, new universes might bud off from our own, new regions of space might connect through wormhole tunnels, new dimensional frameworks might become accessible. These possibilities remain theoretical, at the frontier of modern physics. We cannot currently observe directly what happens beyond a black hole's event horizon, and our theories of quantum gravity, needed to fully describe the extreme conditions near singularities, remain incomplete. Yet the persistent appearance of these cosmic bridges in our mathematical models, emerging from multiple theoretical approaches, suggests they represent more than mere speculation. They point toward a cosmos more complex, more interconnected, more multi-layered than our conventional three-dimensional perspective indicates. Black holes remind us that the boundary of the observable universe is not the end of reality, that what lies beyond might be accessible not by traveling ever greater distances in our familiar space, but by passing through these extraordinary cosmic objects where space and time themselves are warped beyond recognition. They invite us to expand our cosmic perspective, to consider that beyond might not be about distance at all, but about passing through natural gateways in the fabric of reality itself, where the fabric tears, where space and time reach their limits, where our conventional notions of here and elsewhere break down. There, perhaps, new realms begin, new universes unfold, new dimensional frameworks open up. The study of these cosmic bridges continues at the intersection of observation and theory, of mathematics and philosophy, of what we can detect and what we can only infer. It reminds us that the cosmos is not only stranger than we imagine, but perhaps stranger than we can imagine, with connections and passages that transcend our familiar notions of space and time. Black holes, these darkest objects in the cosmos, might ironically be the brightest beacons pointing toward realms beyond our universe, cosmic bridges leading to new frontiers of reality waiting to be explored. Perhaps there is nothing beyond, not even space to hold it. Throughout our journey exploring what might lie beyond the universe, we've considered various extensions of space, infinite universes, multiple dimensions, cosmic bridges through black holes. But now we arrive at perhaps the most profound question of all. What if the concept of beyond itself breaks down? What if space is not a fundamental container, but an emergent property, a relationship between more basic elements? What might lie beyond space itself? To approach this question, we must first reconsider our intuitive understanding of space. In everyday experience, space seems obvious and fundamental, an empty container in which objects exist and events occur. It appears to be a stage on which the cosmic drama unfolds, independent of the actors and props it contains. But modern physics has systematically dismantled this simple picture. Einstein's theories of relativity revealed that space is not absolute, but relative, not fixed, but dynamic, not independent of time, but woven together with it into a four-dimensional fabric called spacetime. This fabric bends and warps in response to matter and energy, creating what we experience as gravity. In this relativistic framework, space is not simply a container, but an active participant in physical processes. The presence of a massive object like the Sun curves the spacetime around it, causing planets to orbit not because of some mysterious force acting across a void, but because they follow the natural contours of curved spacetime. This insight, that space itself has physical properties, that it can bend, stretch, and ripple, was revolutionary. It suggested that space is not a given, not a necessary backdrop for existence, but a physical system that evolves and interacts, that emerged from earlier cosmic conditions and continues to develop. Quantum mechanics pushed this revolution further. At the subatomic scale, space becomes even stranger, filled with quantum fields that permeate everything, subject to uncertainty principles that limit what can be precisely measured, populated by virtual particles that briefly flash into existence from pure vacuum energy. In the quantum realm, the apparently empty vacuum of space is actually a seething cauldron of activity, with quantum fields constantly fluctuating, particles and antiparticles momentarily appearing and annihilating each other, energy borrowing briefly from the future according to Heisenberg's uncertainty principle. These quantum effects suggest that space at its most fundamental level is nothing like our intuitive picture. It's not an empty stage, but a complex, dynamic system of interacting fields, a probability landscape rather than a definite arena, a web of potential rather than a fixed container. When we combine these relativistic and quantum insights, as theoretical physicists have been attempting to do for decades in the quest for a theory of quantum gravity, even more profound possibilities emerge. Space, and time along with it, might not be fundamental at all, but emergent properties arising from deeper, more basic elements of reality. This concept of emergence is crucial for understanding what might lie beyond space. Emergence occurs when collective behaviors arise that are different from, and not obviously predictable from, the behaviors of constituent parts. Temperature, for instance, emerges from the collective motion of molecules, even though individual molecules don't have a temperature. Similarly, consciousness emerges from billions of neurons firing together, even though individual neurons aren't conscious. Could space itself be an emergent phenomenon, arising from something more fundamental that is not spatial in nature? Several approaches to quantum gravity suggest this provocative possibility. These are not atoms in the chemical sense, but fundamental quanta of spatial volume, connected through a complex network of relationships. In this picture, the smooth, continuous space we experience emerges from this discrete quantum network when viewed at larger scales, much as a seemingly smooth image on a digital screen emerges from discrete pixels when viewed from a distance. What lies beyond space would then be this more fundamental network of quantum relationships, not spatial in itself, but giving rise to space as an emergent property. Another approach comes from string theory, which suggests that elementary particles are actually tiny, one-dimensional vibrating strings. Different vibration patterns create different particles, and these strings exist in a higher dimensional space, most of which is compactified or curled up beyond our detection. In some versions of string theory, space and time themselves emerge from the collective behavior of these strings and their interactions. The fundamental reality would be the strings and their mathematical relationships, not the space they appear to occupy, which would be a kind of collective illusion constructed by our macroscopic perspective. A third approach comes from causal set theory, which proposes that space-time is fundamentally discrete and that the essential relationship is not spatial distance, but causal connection, which events can influence which other events. Space and time, as we know them, would emerge from this more basic causal structure, a vast network of cause and effect relationships among discrete events. Yet another perspective comes from quantum information theory, particularly the holographic principle. This principle suggests that all the information contained in a volume of space can be represented on a boundary enclosing that space, similar to how a two-dimensional hologram can create the illusion of a three-dimensional image. In the holographic framework, space itself might be a kind of projection or encoding of information that exists in a different, more fundamental form. What we experience as spatial reality might be a translation of quantum information existing in a non-spatial form, similar to how the three-dimensional image from a hologram is encoded in a pattern on a two-dimensional surface. These various approaches to quantum gravity and the nature of space share a common suggestion. Space, as we experience it, is not fundamental but emergent, not a basic container, but a construct arising from deeper, non-spatial elements of reality. What lies beyond space would then be these more fundamental elements: quantum networks, vibrating strings, causal sets, or encoded information, from which space itself emerges. This perspective dramatically reshapes our understanding of what it might mean for something to be beyond the universe. If space itself is emergent, then what lies beyond space is not more space, not a spatial outside to our cosmos, but something more fundamental, something from which space itself arises. What are the basic non-spatial elements from which space emerges? What is the code, the program, the quantum information from which our experience of three-dimensional space unfolds? This shift from beyond to beneath or underlying may seem abstract, but it has profound implications for our understanding of reality. It suggests that our spatial intuitions, powerful as they are for navigating the macroscopic world, may mislead us when applied to the most fundamental questions about existence. Just as our intuitive notion of solid objects breaks down when we discover they're mostly empty space with tiny nuclei and electrons, our intuitive notion of space itself breaks down when we discover it might be an emergent property of something more fundamental and not recognizably spatial. This perspective also connects to philosophical traditions that have long questioned the fundamental nature of space. From Plato's forms to Kant's transcendental idealism to modern phenomenology, philosophers have explored the possibility that space as we experience it is a construction of consciousness, a way our minds organize and interpret more fundamental aspects of reality. Modern physics doesn't necessarily endorse these philosophical views, but it does suggest that space as we experience it is not the whole story, not the bottom layer of reality. What we perceive as spatial relationships might be translations of more fundamental relationships that are not inherently spatial. The idea that space itself emerges from something more fundamental also has implications for cosmology and the origin of the universe. The Big Bang in this perspective would not be the beginning of everything, but the beginning of space and time as we know them, emerging from a more fundamental, non-spatial reality. What existed before the Big Bang would then not be a prior state in time, since time itself began with the Big Bang, but the non-temporal, non-spatial foundation from which space and time emerged. The question becomes not what happened before the Big Bang, but what timeless, spaceless reality underlies the emergence of our space-time universe. Some theoretical frameworks suggest possibilities for this more fundamental reality. Certain approaches to quantum cosmology, particularly the no-boundary proposal developed by Stephen Hawking and Jim Hartle, suggest that the universe emerged from a state where time as we know it did not exist. where the distinction between space and time blurs in a quantum fog of possibilities. In this picture, asking what existed before the universe is like asking what lies north of the North Pole. It's a question that assumes a spatial or temporal framework that doesn't apply to the situation. There is no before in the conventional sense, just as there is no north from the North Pole. What exists is a different kind of reality, one not organized by our familiar notions of space and time. Other approaches, like eternal inflation or cyclical cosmological models, suggest that our universe might be one episode in a larger process that has always existed, not in time as we know it, but in some more fundamental framework. What lies beyond our universe would then be other episodes or cycles or bubbles in this timeless, spaceless process. These various frameworks share a common insight. When we reach the limits of our universe, the boundaries of space and time as we know them, what we find is not more of the same, not an extension of our familiar dimensions, but something qualitatively different, something more fundamental from which our familiar reality emerges. This emergence perspective also sheds new light on the multiverse concept. Different universe bubbles or branches might not exist alongside each other in some higher space, but might be different emergent patterns from the same underlying non-spatial reality, different solutions to the same fundamental equations, different expressions of the same quantum wave function. The multiverse would then be not a collection of spatial regions separated by vast distances or higher dimensions, but a family of emergent patterns arising from the same non-spatial foundation, related not by spatial proximity, but by their common origin in this more fundamental reality. This perspective on what lies beyond space itself connects to some of the deepest questions in physics and philosophy. What is the nature of reality at its most fundamental level? What are the basic building blocks not just of matter and energy, but of space and time themselves? How does the familiar world of our experience emerge from these more fundamental elements? These questions push against the limits of our current understanding, the boundaries between established science and speculative theory, the frontier where physics meets philosophy. They remind us that our intuitive notions of reality, powerful as they are for navigating everyday life, may be inadequate for comprehending the deepest nature of existence. Yet remarkably, despite these limitations, we can still approach these questions through a combination of mathematical modeling, theoretical physics, philosophical analysis, and empirical constraints. We can still develop meaningful frameworks for understanding what might underlie space itself, what might exist beyond the spatial universe as we know it. These frameworks remain speculative, at the frontier of physics and cosmology. We cannot directly observe the quantum networks, vibrating strings, causal sets, or encoded information that might underlie space. Our observations are always mediated by space itself, filtered through the very phenomenon we're trying to look beyond. But this doesn't mean these speculations are merely philosophical or untestable. Theoretical frameworks for what underlies space make predictions about the behavior of space at its limits, in the extreme conditions of the early universe, near black hole singularities, or at the smallest quantum scales. These predictions can be tested, at least indirectly, through astronomical observations, gravitational wave detections, or particle physics experiments. For instance, if space emerges from a discrete quantum network, as loop quantum gravity suggests, there might be subtle quantum fluctuations in the fabric of space, tiny deviations from perfect continuity that could affect the propagation of light across vast cosmic distances. Similarly, if space emerges holographically from information encoded on a boundary, there might be correlations in quantum fields that reflect this holographic structure. Scientists continue to develop more sophisticated experiments and observations to search for such signatures, pushing the boundaries of what we can detect, striving to glimpse the foundations beneath the spatial reality we directly experience. Beyond these scientific approaches, the question of what lies beyond space itself also invites philosophical and even spiritual contemplation. Many traditions have suggested that ultimate reality transcends space and time, that the deepest nature of existence is not spatial or temporal but something more fundamental. From the Tao that cannot be told in ancient Chinese philosophy, to Brahman as the underlying reality in Vedanta, to the spaceless, timeless ground of being. In certain Western philosophical and theological traditions, humans have long intuited that space as we experience it might not be the final word, not the deepest level of reality. Modern physics, with its suggestion that space emerges from something more fundamental, gives new resonance to these ancient intuitions. It doesn't necessarily validate any particular spiritual or philosophical tradition, but it does suggest that the intuition of a reality beyond space has a certain coherence, a potential alignment with our best scientific understanding. Perhaps there is nothing beyond, not even space to hold it. Perhaps what we seek beyond the universe is not an exterior realm, but a more fundamental level of existence, not a spatial outside, but an underlying reality from which space itself emerges. Perhaps the ultimate context for our universe is not a larger container, but a deeper foundation, not an encompassing superspace, but an underlying quantum reality. This perspective invites us to transcend our spatial intuitions, to think beyond the limitations of our three-dimensional experience, to consider realities that cannot be visualized in conventional spatial terms, but can be described mathematically and apprehended conceptually. It reminds us that the cosmos is not only vaster than we imagine, but perhaps structured in ways that transcend our spatial and temporal categories entirely. The reality beyond space might not be out there at all, but underlying everything, pervading all that exists, the foundation from which space itself springs. In contemplating what lies beyond space itself, we reach the limits, not just of our knowledge, but of our conceptual frameworks, our linguistic categories, our imaginative capacities. We approach mysteries that may never be fully resolved, questions that may always retain an element of wonder and uncertainty. Yet in this uncertainty, in this reaching beyond what we can easily visualize or comprehend, we participate in one of humanity's most profound endeavors, the quest to understand the ultimate nature of reality, to glimpse the deepest foundations of existence, to comprehend not just our place within the cosmos, but the very nature of the cosmos itself. Perhaps there is nothing beyond, not even space to hold it. And in that insight, we find not limitation but liberation, not an end to our cosmic journey but a new beginning, an invitation to explore not just the vast expanses of space, but the profound depths from which space itself emerges. We may not see beyond, but we might still hear it in the oldest light. Throughout our journey, exploring what might lie beyond the universe, we've ventured deep into theoretical realms, considering possibilities from infinite cosmic expansion to emergent space itself. But what evidence do we actually have for any of these possibilities? What observations might help us distinguish between these different models of what lies beyond our cosmic horizon? While we cannot directly observe what lies beyond the observable universe by definition, we might still detect indirect signatures, subtle echoes of other realms that leave imprints on what we can observe. Let's explore the potential evidence for what might lie beyond, from faint patterns in ancient radiation to cosmic collisions that could shake our universe from outside. Our most powerful window into the early universe, and potentially what lies beyond, is the cosmic microwave background radiation, or CMB. This faint afterglow of the Big Bang permeates all of space, providing a snapshot of the universe when it was just 380,000 years old. The CMB has been called the oldest light in the universe, photons that have been traveling through space for nearly 14 billion years before reaching our detectors. The Planck and WMAP satellites have mapped this radiation in exquisite detail, revealing tiny temperature fluctuations, just 1 part in 100,000, that correspond to the seeds from which all cosmic structure eventually grew. These fluctuations contain a wealth of information about the early universe and, potentially, about what might lie beyond. One intriguing possibility is that our universe might have collided with another bubble universe in the inflationary multiverse. Such a collision would create a distinctive pattern in the CMB, a circular or disk-like region with slightly different temperature statistics than the surrounding sky. It would be like a cosmic bruise, a signature of contact with another universe. Cosmologists have searched for such patterns in the CMB data, looking for statistical anomalies that might indicate a bubble collision. While some researchers have claimed to find potential candidates, none has been confirmed with high statistical significance. These searches continue as data analysis techniques improve, offering the tantalizing possibility of finding direct evidence for the existence of other universes. Another potential signature comes from the large-scale pattern of CMB fluctuations. According to standard inflationary theory, these fluctuations should be statistically uniform across the sky, with no preferred directions or scales. But some analyses have suggested possible anomalies, including a mysterious alignment of the largest fluctuations along what has been called the axis of evil, and an unexplained cold spot in the southern celestial hemisphere. These anomalies might be statistical flukes or systematic effects in the data, but they might also be signatures of cosmic structures beyond our observable universe affecting our own, or of exotic physics during the inflationary epoch, or even of a particular topology of space that causes the universe to connect back on itself in unexpected ways. For instance, if the universe has a finite size and a non-trivial topology, like a three-dimensional torus, we might observe a pattern of matched circles in the CMB, regions with correlated temperature fluctuations, because they represent the same physical locations seen from different directions. Searches for such patterns have not found definitive evidence yet, but they continue to constrain the possible size and shape of the universe. Another potential source of evidence comes from the specific statistical properties of the CMB fluctuations. The standard model of cosmic inflation predicts that these fluctuations should follow a nearly Gaussian distribution, meaning the pattern of hot and cold spots should have specific statistical properties. Deviations from this Gaussian pattern might indicate exotic physics during inflation, potentially related to structures beyond our observable universe. Current measurements find that the CMB is remarkably close to Gaussian, but with intriguing hints of potential non-Gaussianity at the limits of observational precision. Future CMB experiments with greater sensitivity might reveal clearer signatures of exotic physics or structures beyond our cosmic horizon. Beyond the CMB, another potential source of evidence comes from the distribution of galaxies on the largest scales. Our observations reveal a cosmic web of galaxy clusters and superclusters separated by vast voids, creating a sponge-like structure throughout the observable universe. The statistical properties of this distribution, how galaxies cluster together at different scales, contain information about the fundamental properties of space and potentially what lies beyond. For instance, if our universe is one bubble in a multiverse, the process that formed it might leave subtle imprints on the largest scales of cosmic structure. Similarly, if space has a non-trivial topology, connecting back on itself in higher dimensions, this might create distinctive patterns in how galaxies cluster at the largest observable scales. Current galaxy surveys, like the Sloan Digital Sky Survey, have mapped millions of galaxies, revealing the cosmic web in unprecedented detail. Future surveys, like the Legacy Survey of Space and Time at the Vera C. Rubin Observatory, will map billions of galaxies across even larger volumes, potentially revealing statistical patterns that could distinguish between different models of what lies beyond our cosmic horizon. Gravitational waves offer another promising avenue for detecting signals from beyond our observable universe. These ripples in space-time, first directly detected in 2015, open a new window on the cosmos, allowing us to observe phenomena invisible to traditional telescopes. Of particular interest are primordial gravitational waves, ripples produced during the inflationary epoch immediately after the Big Bang. These waves would have been stretched by cosmic expansion to incredible wavelengths, creating a background hum of gravitational radiation permeating the universe. The specific properties of this primordial gravitational wave background, its strength, spectral shape, and potential anisotropies, depend on the details of inflation and potentially on structures beyond our observable universe. For instance, collisions with other bubble universes might create distinctive patterns in this background, offering another potential signature of the multiverse. Scientists are searching for these primordial gravitational waves through their effects on the polarization of the CMB and through direct detection with increasingly sensitive gravitational wave observatories. The detection of primordial gravitational waves would not only confirm the theory of cosmic inflation, but might also provide information about what lies beyond our cosmic horizon. Another potential source of evidence comes from the details of cosmic inflation itself. The specific pattern of fluctuations we observe in the CMB and in the distribution of galaxies contains information about the inflationary process that created our observable universe. Different models of inflation predict slightly different patterns, and some of these models naturally connect to the multiverse concept. For instance, in the eternal inflation scenario, where inflation continues indefinitely in some regions while stopping in others to form bubble universes, we might expect specific signatures in the spectrum of fluctuations we observe. The details of how inflation ended in our region could tell us whether it continues elsewhere, forming other universes beyond our cosmic horizon. Current observations favor relatively simple models of inflation, but they don't definitively rule out more complex scenarios that naturally lead to a multiverse. Future observations with more precise measurements of the CMB and cosmic structure might help distinguish between these different inflationary models and their implications for what lies beyond. Black holes offer yet another potential window into realms beyond our observable universe. As we explored in a previous chapter, the extreme warping of space-time near a black hole's singularity might create connections to other regions of space-time, or even other universes entirely. While we cannot directly observe beyond a black hole's event horizon, we might detect indirect signatures of such connections. For instance, if black holes connect to other universes or regions of space-time, matter and energy falling into a black hole in our universe might emerge elsewhere, creating observable effects in the receiving region. Similarly, matter and energy from beyond our universe might emerge from what we perceive as black holes, potentially creating distinctive signatures in their behavior. Such signatures might include unexpected patterns in the Hawking radiation emitted by black holes as they slowly evaporate, or anomalous gravitational wave signals from black hole mergers, or unusual behaviors in the accretion disks surrounding black holes. While current observations haven't found definitive evidence for such exotic phenomena, they remain an area of active research and theoretical development. Quantum entanglement, the spooky connection between particles that Einstein called spooky action at a distance, might provide another indirect window into what lies beyond our observable universe. In quantum mechanics, particles can become entangled such that the state of one particle is instantaneously correlated with the state of another, regardless of the distance between them. Some speculative theories suggest that quantum entanglement might extend beyond our observable universe, connecting particles here with counterparts in regions that we cannot directly observe. This cosmic-scale entanglement might leave subtle signatures in the quantum fields that permeate our universe, potentially detectable through precise measurements of quantum systems. While this possibility remains highly speculative and at the frontier of quantum gravity research, it represents another potential avenue for detecting indirect evidence of what might lie beyond our cosmic horizon. The specific values of fundamental physical constants and parameters offer yet another potential source of evidence. The standard model of particle physics contains about 25 free parameters, the masses of elementary particles, the strengths of fundamental forces, and so on, whose values are not predicted by the theory, but must be measured experimentally. Similarly, cosmology has its own set of fundamental parameters, including the density of matter and energy in the universe, the rate of cosmic expansion, and the amplitude of primordial fluctuations. Together, these parameters define the specific properties of our universe, distinguishing it from other possible universes with different parameter values. The observed values of these parameters seem remarkably fine-tuned for the existence of complex structures and eventually life. Small changes to many of these values would result in a universe where atoms, stars, or galaxies could not form. This apparent fine-tuning has led some physicists to invoke the multiverse and the anthropic principle. If a vast multiverse exists with different regions having different parameter values, we naturally find ourselves in one of the rare regions compatible with our existence. While this anthropic explanation remains controversial, it provides a potential way to understand the specific values we observe without requiring a more fundamental theory to predict them uniquely. If correct, it would provide indirect evidence for the existence of a multiverse beyond our observable horizon. Future observations might help clarify this picture by more precisely measuring these fundamental parameters and potentially revealing patterns or relationships among them that could distinguish between different explanations for their values. For instance, if a more fundamental theory can be developed that uniquely predicts these values without invoking the multiverse, it would weaken the anthropic argument for what lies beyond. Laboratory experiments might provide additional windows into what lies beyond our observable universe. Particle accelerators like the Large Hadron Collider, LHC, probe the fundamental structure of matter and energy at the highest accessible energies, potentially revealing signatures of extra dimensions, supersymmetry, or other exotic physics that connect to the multiverse concept. For instance, if our universe exists as a brane in a higher dimensional bulk space, with other branes potentially harboring other universes, there might be detectable consequences in high-energy particle collisions. Particles might momentarily leave our brane and enter the bulk space before returning, creating distinctive energy and momentum signatures in detectors. Similarly, if the vacuum state of our universe is not the true ground state but a metastable configuration, as suggested by certain particle physics models, it might eventually decay to a lower energy state through quantum tunneling. This vacuum decay would propagate outward at the speed of light, fundamentally altering the laws of physics in affected regions. A truly apocalyptic scenario. Laboratory experiments can help constrain the stability of our vacuum and, by extension, provide information about the landscape of possible vacuum states that might exist beyond our cosmic horizon. Theoretical consistency and mathematical elegance provide another form of indirect evidence for what might lie beyond. While not observational in the conventional sense, the internal consistency and explanatory power of our mathematical models offer clues about the underlying structure of reality, including what might exist beyond our observable reach. For instance, string theory naturally leads to the concept of a vast landscape of possible vacuum states, corresponding to different ways of compactifying the extra dimensions required by the theory. While this landscape is not directly observable, its emergence from a mathematically consistent framework provides a theoretical foundation for the multiverse concept. Similarly, eternal inflation emerges naturally from attempts to solve problems with early universe cosmology, such as the flatness and horizon problems. The fact that this inflationary process, once started, generically continues indefinitely in some regions, while stopping in others to form bubble universes, suggests a multiverse structure as a natural consequence of our best cosmic origin theories. The holographic principle, emerging from studies of black hole thermodynamics and developed into the ADS-CFT correspondence in string theory, suggests a deep connection between gravity in a volume of space and quantum field theory on the boundary of that space. This holographic relationship hints at a more fundamental description of reality that might transcend our conventional notions of space and what lies beyond it. These theoretical frameworks, while not providing direct observational evidence for what lies beyond our universe, offer coherent mathematical structures that naturally incorporate extra dimensions, multiple universes, or non-spatial foundations for reality. Their internal consistency and explanatory power lend credibility to the possibilities they suggest, even as direct observational confirmation remains elusive. As we look to the future, several upcoming observatories and experiments might provide new insights into what lies beyond our cosmic horizon. The James Webb Space Telescope, launched in 2021, will observe the earliest galaxies, providing new constraints on cosmic evolution and the processes that shaped our observable universe. The Laser Interferometer Space Antenna, LISA, planned for the 2030s, will detect gravitational waves from a wider range of sources than current observatories, potentially including primordial signals from the early universe. Next-generation CMB experiments like CMBS-4 and potential space missions like PICO will map the cosmic microwave background with unprecedented precision, potentially revealing subtle signatures of exotic physics or structures beyond our observable universe. New galaxy surveys, like those from the Nancy Grace Roman Space Telescope and the Euclid mission, will map cosmic structure across vast volumes, constraining the largest scale properties of the universe. Future particle accelerators, with energies beyond the current LHC, might probe deeper into the fundamental structure of matter and force, potentially revealing connections to extra dimensions or multiverse models. Advanced quantum experiments might test the foundations of quantum mechanics and its connections to gravity, potentially shedding light on the most fundamental aspects of reality. These future observations and experiments might not directly show us what lies beyond our cosmic horizon, but they could provide indirect evidence, constraining the possibilities and guiding our theoretical understanding. They represent humanity's ongoing effort to push the boundaries of knowledge, to glimpse what might exist beyond the limits of direct observation. Despite these impressive technological achievements and theoretical developments, we must acknowledge the fundamental limits to what we can know about what lies beyond our universe. The cosmic horizon represents a causal boundary, not just a current technological limitation. Regions of space receding faster than light due to cosmic expansion are forever beyond our observational reach, no matter how advanced our instruments become. Similarly, if other universes exist in the multiverse, they might be fundamentally disconnected from our own, with no causal interaction possible. We might infer their existence indirectly through theoretical models or subtle signatures in what we can observe, but direct observation remains impossible in principle. These fundamental limits don't mean we should abandon the search for what lies beyond. Rather, they remind us to be appropriately modest in our claims, to distinguish between well-established observations, reasonable theoretical inferences, and more speculative possibilities. They invite us to develop increasingly sophisticated indirect methods, to find creative ways to test theories that make predictions about the unobservable. The question of what lies beyond our universe connects to deep philosophical issues about the nature of scientific knowledge, the relationship between mathematics and physical reality, and the limits of human understanding. It challenges us to consider what constitutes evidence, how we evaluate competing theoretical frameworks, and how we navigate the boundary between physics and metaphysics. In this exploration, we find not just scientific questions, but philosophical ones. Can something exist if it cannot in principle be observed? Does mathematics discover pre-existing structures or invent useful abstractions? How do we evaluate theories that make predictions about the unobservable? What constitutes an explanation in cosmology? And when should we be satisfied with our understanding? These questions have no simple answers, but in grappling with them, we develop more nuanced approaches to the deepest cosmic mysteries. We learn to hold multiple possibilities in mind simultaneously, to evaluate evidence within theoretical frameworks while remaining open to alternative interpretations, to push the boundaries of knowledge while acknowledging its limits. In this ongoing endeavor, the search for echoes and evidence of what might lie beyond our universe represents one of humanity's most profound intellectual challenges. It combines cutting-edge observation with sophisticated mathematics, philosophical analysis with technological innovation, empirical constraint with theoretical creativity. We may not see beyond, but we might still hear it in the oldest light. We might detect its influence in the patterns of cosmic structure, in the ripples of gravitational waves, in the behavior of quantum fields, in the mathematical consistency of our best theories. These indirect signals, these subtle echoes of realms beyond our direct observation, guide our ongoing exploration of the greatest cosmic mysteries. As we continue this exploration, we remember that the history of cosmology has been one of continuously expanding horizons. What was once thought to be the entire cosmos, the Earth, the solar system, the Milky Way, has repeatedly been revealed as just one small part of a much larger whole. Perhaps our observable universe will follow this same pattern, eventually understood as just one region of a much larger, more diverse, more surprising reality. The echoes and evidence we detect today represent just the beginning of this continuing journey of discovery, the first hints of what might lie beyond the current limits of our cosmic understanding. In listening carefully to these faint signals, in developing theories to explain them, in designing new observations to test these theories, we participate in humanity's greatest intellectual adventure, the quest to comprehend the true nature and extent of the cosmos we inhabit. We ask because we exist, and existence demands wonder. Throughout our journey, exploring what might lie beyond the universe, we've ventured through realms of cosmology, quantum physics, and theoretical mathematics. But our exploration would be incomplete without considering the philosophical dimensions of this great question. It's not merely scientific. It touches on fundamental philosophical issues about existence, meaning, and the limits of human understanding. When we ask what lies beyond the universe, We're not just asking about distant regions of space or exotic theoretical constructs. We're asking about the nature of reality itself, about boundaries and infinities, about what it means for something to exist, about our place in the cosmic scheme. These questions have engaged philosophers since ancient times, long before modern science provided its remarkable but still limited insights. Let's begin with perhaps the most basic philosophical question in this domain. What does it mean for something to exist beyond the universe? This question hinges on our definition of existence itself. In classical philosophy, from Aristotle through medieval thought, existence was often understood as actual presence in the world of experience, or at least potential detectability. Something exists if it has causal powers within our reality, if it can, in principle, affect what we observe. By this criterion, anything truly beyond our universe, causally disconnected from our reality, unable in principle to interact with our world, would not exist in the relevant sense. It might have what philosophers call subsistence rather than existence, a kind of shadow being outside the realm of actual things. But modern philosophy and science have expanded our notions of existence. Mathematical Platonism suggests that mathematical structures exist in some non-physical, but nonetheless real sense, independent of human minds. Some interpretations of quantum mechanics propose that unobserved quantum states or parallel quantum worlds have a kind of existence despite their inaccessibility to direct observation. These expanded notions of existence provide conceptual space for things that might lie beyond our universe in various senses. Other bubble universes in the multiverse, higher dimensional spaces in which our cosmos is embedded, non-spatial foundations from which space itself emerges. These realms might exist even if we cannot directly observe them, even if they have no causal influence on what we can measure. This leads to another philosophical question. Can something meaningfully exist if it cannot in principle be observed? This touches on long-standing debates about scientific realism versus instrumentalism, about the relationship between our theories and the reality they purport to describe. Scientific realists argue that successful theories tell us about what actually exists, even if some aspects of that reality are not directly observable. The electron, for instance, was accepted as real long before technology allowed anything approaching direct observation, because its existence elegantly explained a wide range of phenomena. By this reasoning, if the multiverse concept successfully explains features of our observable universe, we might reasonably infer its reality despite our inability to directly observe other universes. Instrumentalists, by contrast, view scientific theories primarily as tools for making predictions about observable phenomena, remaining agnostic about whether unobservable entities really exist in any deeper sense. From this perspective, concepts like the multiverse might be useful mathematical devices without necessarily corresponding to additional realities beyond our cosmos. Between these positions lie various forms of structural realism, which suggest that what science primarily reveals is not the intrinsic nature of reality, but its structural or relational features. By this view, the mathematical structures of our theories might capture something real about what lies beyond the observable universe, even if the intrinsic nature of that reality remains inaccessible. These questions about existence and observation connect to another philosophical dimension of our inquiry, the relationship between mathematics and physical reality. Many of the concepts we've explored, higher dimensions, infinite multiverses, emergent space, emerge naturally from the mathematics we use to describe the observable universe. When this mathematics points to structures beyond what we can observe, should we view these as real features of the cosmos or merely as artifacts of our mathematical models? The history of physics reveals many cases where mathematics led the way to new aspects of physical reality. Einstein's general relativity predicted black holes and cosmic expansion before either was observed. The Dirac equation predicted antimatter before positrons were discovered. The Higgs mechanism was mathematically proposed decades before the Higgs boson was detected. This track record lends some credence to the notion that when our best mathematical models consistently point to structures beyond the observable universe, these structures might actually exist in some meaningful sense. The mathematics might be revealing genuine features of reality, not just useful fictions. Yet caution is warranted. Not all mathematically elegant theories turn out to correspond to physical reality. the history of science also includes beautiful theories that nature ultimately rejected. Mathematics provides possibilities, maps of what might exist, but only observation can tell us which mathematical structures actually describe our reality. This tension between mathematical possibility and observational constraint lies at the heart of contemporary cosmology. Our mathematical models consistently suggest realities beyond what we can observe, infinite spaces, multiple universes, higher dimensions, but our ability to test these suggestions remains limited by fundamental physical constraints, not just current technology. These limitations lead to profound questions about the nature of scientific explanation and understanding. Traditional scientific explanation involves deriving observed phenomena from more fundamental principles that can be independently tested. But when addressing what lies beyond the observable universe, this standard approach falters. We cannot independently test claims about regions permanently beyond our observational reach. Does this mean questions about what lies beyond the universe are inherently unscientific? Not necessarily. Science has always operated at the boundary between the known and the unknown, developing methods to infer the unobserved from the observed, to extend understanding beyond direct experience. The challenge with what lies beyond the universe is not that these questions are unscientific in principle, but that they push scientific methodology to its limits, requiring more indirect approaches and more tentative conclusions. This methodological challenge connects to deeper philosophical questions about the limits of human understanding. Throughout history, thinkers have debated whether there are fundamental boundaries to what humans can know, whether aspects of reality might forever remain beyond our cognitive grasp. Immanuel Kant argued that we can never know things in themselves, only how they appear to beings with our particular cognitive structure. Applied to cosmology, this Kantian perspective suggests we might be inherently limited in our ability to comprehend what lies beyond the observable universe, not just by technological constraints, but by the very nature of human understanding. Yet the history of science can be read as a progressive transcendence of apparent cognitive limitations. Concepts that once seemed literally unthinkable, atoms, curved space, quantum superposition, have become parts of our scientific worldview, comprehensible through appropriate mathematical frameworks, even when they defy everyday intuition. This suggests that while human understanding certainly has limits, these limits can expand through the development of new conceptual tools, new mathematics, new modes of scientific reasoning. The question of what lies beyond the universe might not be forever unanswerable, even if it currently stretches our cognitive and methodological capabilities to their utmost. Another philosophical dimension of our cosmic inquiry concerns boundary conditions and ultimate explanations. If there is something beyond our universe, what lies beyond that? And beyond that, do we face an infinite regress of ever larger contexts, or is there some ultimate reality that requires no further explanation? This question echoes ancient philosophical debates about first causes and ultimate foundations. Aristotle proposed an unmoved mover, a necessary being that causes without being caused. Various theological traditions posit God as the ultimate ground of existence, requiring no explanation beyond divine nature itself. Modern cosmology seeks self-contained models that might explain the universe's origin without reference to anything external. Yet the challenge persists. Any proposed final theory or ultimate context raises the question, why this reality rather than another? Why these fundamental laws or structures rather than different ones? The principle of sufficient reason, championed by Leibniz, suggests everything must have an explanation. But can there be a sufficient explanation for the most fundamental aspects of reality itself? Some philosophers and cosmologists have proposed that reality might ultimately be self-explanatory through a kind of logical or mathematical necessity. Perhaps the fundamental structure of reality is the only logically consistent possibility, the unique solution to some set of basic constraints or equations. Others suggest that asking for an explanation of the most fundamental features of reality might be a category error, like asking what's north of the North Pole. Perhaps, at the deepest level, existence simply is, without further explanation or foundation needed. This connects to questions about necessity and contingency in the structure of reality. Are the fundamental laws and parameters of our universe necessary, the only logically possible set? Or are they contingent, just one possibility among many that happen to be realized in our cosmic patch? The multiverse concept suggests contingency, that the specific details of our observable universe represent just one solution among many to the underlying equations of physics. Different regions of the multiverse would have different properties, different physical laws, different possibilities for structure and life. This contingency view has profound implications for how we understand our place in the cosmos. If our universe is just one among many, with its specific properties arising from random processes rather than necessity, then the apparent fine-tuning of physical constants for life becomes less mysterious. In a vast enough multiverse containing universe bubbles with all possible properties, some will inevitably have the right conditions for life, and those are necessarily the ones in which observers like us evolve to ask these questions. This application of the anthropic principle remains controversial, with critics arguing it represents a retreat from the traditional scientific goal of finding unique explanations for observed phenomena. But it highlights how the question of what lies beyond our universe connects to our understanding of our own existence and its significance. This brings us to perhaps the most profound philosophical dimension of our cosmic inquiry, the implications for meaning, purpose, and human significance. If there is something beyond our universe, whether infinite space, multiple universe bubbles, higher dimensions, or non-spatial foundations, what does this mean for our sense of place and purpose in reality? Throughout history, cosmic models have influenced how humans understand their significance. Ancient geocentric models placed humanity at the physical center of creation, seemingly affirming our cosmic importance. The Copernican revolution displaced Earth from this central position, triggering what has been called the first in a series of discenterings that have progressively relocated humanity from the spatial center of reality. The discovery of galaxies beyond the Milky Way further diminished our cosmic centrality. If the multiverse exists, this decentering continues. Our entire observable universe becomes just one region among countless others, our physical laws just one possibility among many, our existence just one flowering of complexity in an incomprehensibly vast and diverse reality. Some find this perspective alienating or nihilistic, suggesting it reduces human existence to cosmic insignificance, a mere accident in an indifferent multiverse. Others find it liberating and awe-inspiring, freeing us from the burden of cosmic specialness while connecting us to a reality far grander and more wondrous than earlier conceptions. A more nuanced philosophical approach recognizes that significance need not depend on cosmic centrality or uniqueness. Value and meaning might emerge from complexity, consciousness, and connection rather than from cosmic position or purpose. A multiverse, teeming with diverse realities, doesn't diminish the wonder of our particular existence, but contextualizes it within a grander tapestry of possibilities. This perspective echoes certain existentialist themes. In a universe without inherent meaning or purpose, we create significance through our choices, our connections, our ways of engaging with reality. The vastness beyond our cosmic horizon neither grants nor denies meaning. It simply provides a larger context within which meaning emerges through conscious experience and relationship. Another philosophical dimension concerns the limits of imagination and conceptualization. When we ask what lies beyond the universe, we're trying to conceptualize what might transcend our experiential framework, to imagine what might exist outside the context that makes imagination possible. This creates a fundamental tension. Our concepts and language evolved to describe things within our universe, experiences available to beings with our particular perceptual and cognitive structures. When applied to what might lie beyond, these tools may be inadequate, like trying to describe color to someone born blind, or explain quantum superposition using only classical concepts. Various philosophical and spiritual traditions have grappled with this tension, developing approaches to thinking about what transcends ordinary conceptualization. Negative theology describes the divine by stating what it is not rather than what it is. Zen Buddhism uses koans to push beyond conceptual thinking. Certain mystical traditions emphasize direct experience over conceptual understanding when approaching ultimate reality. Modern physics faces similar challenges. Quantum mechanics and relativity require mathematical frameworks that defy easy translation into ordinary language and intuition. What lies beyond our universe may be similarly resistant to conventional conceptualization, requiring new cognitive approaches, new metaphors, perhaps even new forms of mathematics to adequately grasp. This doesn't mean we should abandon the attempt to understand what lies beyond. Rather, it invites a kind of conceptual humility, a recognition that our current cognitive tools may be limited when addressing the most fundamental cosmic questions. It suggests the need for cognitive innovation, for new ways of thinking that might transcend current limitations. Despite these challenges, the question of what lies beyond the universe remains profoundly important, both scientifically and philosophically. It represents the current frontier of our cosmic understanding, the boundary where established knowledge meets speculative exploration, where empirical science meets philosophical inquiry. In pursuing this question, we continue a journey that has defined humanity, the quest to understand our place in the cosmos, to comprehend the nature of reality itself, to push beyond current horizons toward deeper understanding. This quest has led from Earth-centered models to galactic awareness, from static space to expanding cosmos, from single universe to potential multiverse, each step expanding our cosmic perspective in ways that transform human self-understanding. If there is something beyond our universe, whether infinite space, multiple universe bubbles, higher dimensions, or non-spatial foundations, it reminds us that reality is likely grander, more diverse, more surprising than our current understanding encompasses. It invites both intellectual humility about the limits of our knowledge and intellectual ambition to transcend those limits. This philosophical tension between humility and ambition, between recognizing our limitations and striving to overcome them, characterizes the entire scientific enterprise. It's especially pronounced when we ask about what lies beyond the universe, a question that pushes against the boundaries of what we can observe, conceptualize, and comprehend. Yet we continue to ask, to theorize, to observe, to wonder. We develop more powerful telescopes and particle accelerators, more sophisticated mathematical models, more nuanced philosophical frameworks, all aimed at glimpsing what might lie beyond our cosmic horizon. In this ongoing quest, science and philosophy work together, each informing and challenging the other. Science provides observational constraints and mathematical frameworks. Philosophy offers conceptual analysis and methodological reflection. Together, they advance our understanding of what might lie beyond the universe, even as complete certainty remains elusive. This incompleteness, this tentativeness in our conclusions, shouldn't be seen as failure, but as an invitation to continued exploration. The greatest questions in human inquiry are not those that can be definitively answered, but those that continuously expand our understanding, revealing new dimensions of reality with each advance. The question of what lies beyond the universe stands among these great questions, challenging us to expand not just our knowledge but our ways of knowing, not just our cosmic models, but our conceptual frameworks for understanding reality itself. If there is something beyond the universe, if our cosmic horizon encompasses just a fraction of what exists, what does that mean for us? Perhaps it means that existence itself is more open-ended, more filled with possibility, more wonderfully inexhaustible than we had imagined. Perhaps it means that our cosmic story is not self-contained, but connected to larger contexts, deeper foundations, broader realities than our current understanding encompasses. Or perhaps it means something we cannot yet conceive, something that will emerge only through continued observation, theorizing, and philosophical reflection. The history of cosmology suggests that reality often surprises us, that the universe repeatedly proves stranger and more wonderful than our initial conceptions. What lies beyond our universe may well continue this pattern, revealing realities that transcend our current imaginings, structures and connections we have yet to envision, ways of being that expand our notion of what existence itself encompasses. In contemplating these possibilities, in reaching beyond our cosmic horizon through theory and imagination, we participate in one of humanity's most noble endeavors, the quest to understand our place in the cosmos, to comprehend the nature of reality itself, to expand our vision beyond immediate appearances toward deeper truths. We ask because we exist, and existence demands wonder. It calls us to question, to explore, to push beyond current understanding toward deeper comprehension. In asking what lies beyond the universe, we express something fundamental to human consciousness: the drive to transcend boundaries, to connect with what lies beyond, to understand not just our immediate surroundings, but the ultimate context of our existence. Is not merely scientific, but deeply human. It connects to our search for meaning, our sense of place, our capacity for wonder, our drive to understand. In pursuing this question, we express essential aspects of human consciousness and aspiration. Whether or not we ultimately find conclusive evidence for what lies beyond our cosmic horizon, the journey itself transforms us. It expands our perspective, challenges our assumptions, deepens our appreciation for the cosmos we inhabit and the consciousness with which we contemplate it. In this ongoing journey of discovery, the philosophical dimensions of our cosmic inquiry remind us that the greatest value lies not just in the answers we might find, but in the questioning itself, in the reaching beyond current understanding toward deeper comprehension, in the wonder that drives us to ask what lies beyond. We may never answer it, but in asking, we expand ourselves. As our journey draws to a close, we find ourselves returning to the question that began our exploration: is there something beyond the universe? We've traveled through cosmology and quantum physics, through multiverses and hidden dimensions, through black holes and philosophical reflections. We've contemplated infinite expansion and finite loops, bubble universes and emergent space. After all this exploration, what can we say about our original question? The honest answer is that we don't know with certainty. The universe keeps its deepest secrets well hidden, revealing them only gradually to our persistent questioning. What lies beyond our cosmic horizon remains speculative, a realm where our best theories suggest possibilities, but cannot yet provide definitive answers. Perhaps space extends infinitely, filled with galaxies and stars without end. Perhaps our universe is one bubble among countless others in a vast multiverse. Perhaps extra dimensions curl around every point in space, hidden from our perception but fundamental to reality's structure. Perhaps space itself emerges from something more basic, something not spatial at all. Or perhaps something else entirely, something we have not yet imagined, something that will emerge from future observations and theories, something that will surprise and challenge us as the greatest discoveries always do. What's remarkable is not that these questions remain open, but that we can ask them at all. That we, beings composed of the same atoms as the rest of the cosmos, products of the same cosmic evolution that created stars and galaxies, can develop the conceptual tools to comprehend the universe and even question what might lie beyond it. This capacity for cosmic understanding represents one of the most extraordinary developments in the history of the universe that we know. Through mathematics and observation, through theory and experiment, through reason and imagination, we extend our understanding far beyond the limits of our direct experience. The journey of cosmic discovery continues. New telescopes peer deeper into space and time. New gravitational wave observatories detect ripples in space-time from colliding black holes. New particle accelerators probe the fundamental structure of matter. New mathematical frameworks extend our theoretical understanding, suggesting new possibilities for what might exist beyond our current horizon. Each new discovery expands our cosmic perspective. The history of astronomy has been one of continuously growing horizons, from Earth-centered models to solar systems, to galaxies, to the observable universe itself. Perhaps this pattern will continue, with what we now call the universe eventually understood as just one part of a larger reality. But even if we never definitively answer our original question, the journey itself has value. In asking what lies beyond the universe, we stretch our minds, challenge our understanding, reach for comprehension of the largest scales of reality. We transcend our evolutionary origins, engaging with concepts far beyond anything our ancestors needed for survival. This transcendence, this reaching beyond immediate concerns toward understanding of the whole, represents something profound about human consciousness. It connects to our deepest questioning, our sense of wonder, our drive to comprehend not just our immediate environment, but the ultimate context of our existence. In every culture throughout human history, people have looked to the sky and wondered what lies beyond. They've created myths and cosmologies, built observatories and spacecraft, developed mathematics and physics, all in service of understanding our place in the cosmos, Our modern scientific inquiry continues this ancient quest, with more powerful tools but the same fundamental curiosity, may never receive a final answer. Each generation might develop new frameworks, new observations, new theoretical insights that expand our understanding without completely resolving the mystery. The cosmic horizon might continuously recede as we approach it, revealing new vistas, new questions, new possibilities with each advance. Perhaps that's as it should be. Perhaps the greatest questions are not those that can be definitively answered, but those that continuously expand our understanding, revealing new dimensions of reality with each step. Perhaps the journey of discovery matters more than any final destination of complete knowledge. As we contemplate what might lie beyond our cosmic horizon, we experience a unique form of intellectual vertigo, a sense of both limitation and possibility. We cannot directly observe what lies beyond, yet we can theorize, infer, imagine, reaching beyond our observational limits through mathematics and reason. We are simultaneously humbled by the vastness we cannot fully comprehend and elevated by our ability to contemplate it at all. This tension between humility and intellectual ambition characterizes the entire scientific enterprise, driving progress through the interplay between empirical constraint and theoretical imagination. As we conclude our exploration, let us appreciate both what we know and what remains mysterious. We know the universe is vast beyond everyday comprehension, filled with billions of galaxies. We know it has evolved over nearly 14 billion years from an incredibly hot, dense state to the complex cosmos we observe today. We know space itself expands, and that this expansion is accelerating under the influence of dark energy. But we don't know with certainty what lies beyond our cosmic horizon. We don't know whether space is infinite or finite, whether our universe is unique or one among many, whether reality has hidden dimensions or non-spatial foundations. These questions remain open, inviting continued exploration. In embracing both knowledge and mystery, both understanding and wonder, we adopt the most productive stance toward the cosmos, a stance of informed curiosity, of evidence-based wonder, of rational appreciation for both what we comprehend and what still lies beyond our understanding. Is there something beyond the universe? Perhaps, or perhaps not. But in the space between stars, between questions and dreams, something stirs, something calls. Sleep now, beneath the sky, and drift beyond what you know.